Welcome back to the quiet between the stars. I hope you have found a comfortable place to rest. Tonight, we embark on a journey that spans distances so vast that light itself takes billions of years to cross them. We will travel from our home in the Milky Way, past neighboring galaxies, through the great cosmic web of matter, and finally into the emptiest places in the known universe, the cosmic voids, regions where you could travel for hundreds of millions of light years and encounter almost nothing at all. Consider this: the universe is not evenly filled with galaxies. Instead, matter has gathered into enormous filaments and walls, like soap bubbles pressed together, leaving immense dark spaces between them. The Bota's void alone stretches across 330 million light-years, containing almost no galaxies where thousands should exist. What created these empty expanses? Why does matter cluster while darkness dominates? We will begin here, orbiting our own sun, and slowly pull back through the spiral arms of the Milky Way, past the supermassive black hole at its center, out through the local group, and beyond the Virgo supercluster, until we reach the threshold where galaxies become scarce and the universe grows profoundly silent. If these quiet explorations help you find rest at the end of your day, please consider liking this video and subscribing to the channel. Your support allows us to continue these journeys together. Now let your breathing slow. Let the weight of the day fall away. We are leaving Earth behind, and the cosmos is waiting. In the darkness between worlds, where silence stretches across distances too vast for the human mind to hold, matter begins its slow congregation. A cloud of hydrogen and helium, perhaps 60 light-years across, drifts through the interstellar medium. It has been drifting for millions of years. The gas is cold, barely 10 degrees above absolute zero, and extraordinarily thin, perhaps 1,000 atoms per cubic centimeter, which sounds like a lot until you consider that the air you breathe contains 25 quintillion molecules in the same space. This cloud is, by any terrestrial standard, a vacuum, and yet it contains the raw material for 100,000 suns. Gravity is patient. It does not rush. A slight overdensity in one region of the cloud, perhaps caused by the shock wave of a distant supernova, perhaps by the gravitational tug of a passing star, creates a subtle imbalance. Where there is slightly more matter, there is slightly more gravitational pull. More atoms drift toward the denser region. The process feeds itself. Over hundreds of thousands of years, the cloud begins to collapse inward, fragmenting into smaller knots of gas, each one a potential stellar nursery. At the center of one such knot, pressure builds. As gas falls inward, it converts gravitational potential energy into heat. The core temperature rises, from 10 Kelvin to 100, then 1,000, then 10,000. The collapsing cloud, now called a protostar, begins to glow in infrared light, invisible to human eyes but detectable by instruments like the James Webb Space Telescope. It is not yet a star. It is a promise of one. The protostar continues to contract. Its core temperature climbs past 100,000 Kelvin, then past 1 million. At approximately 10 million Kelvin, something remarkable happens. Hydrogen nuclei, which have been bouncing off each other due to their mutual electromagnetic repulsion, finally possess enough kinetic energy to overcome that barrier. They collide and fuse. 4 hydrogen nuclei become one helium nucleus, and in the process, a tiny amount of mass, about 0.7%, is converted directly into energy according to Einstein's famous equation. This is nuclear fusion. This is the moment a star is born. The energy released by fusion creates an outward pressure that halts the gravitational collapse. The star reaches a state of hydrostatic equilibrium, a delicate balance between the inward pull of gravity and the outward push of radiation pressure. This equilibrium can last for millions or billions of years, depending on the star's mass. A star like the Sun, with a mass of approximately 2 nonillion kilograms, that is 2 followed by 30 zeros, will maintain this balance for about 10 billion years. It is currently 4.6 billion years into its life, roughly middle-aged by stellar standards. Mass determines everything about a star's life. A star with 10 times the Sun's mass burns through its hydrogen fuel not 10 times faster, but roughly 1,000 times faster. This is because the core temperature and pressure scale steeply with mass, and fusion rates are extraordinarily sensitive to temperature. A 10 solar mass star might live only 20 million years before exhausting its fuel. A star with 1/10 the Sun's mass, a red dwarf, burns so slowly and efficiently that it could shine for trillions of years, far longer than the current age of the universe. The Sun converts approximately 620 million metric tons of hydrogen into helium every second. This sounds catastrophic, but the Sun contains enough hydrogen to sustain this rate for billions of years more. The energy produced in the core takes a remarkably long time to reach the surface. Estimates suggest that a photon generated in the solar core may take between 10,000 and 170,000 years to random walk its way to the photosphere, bouncing off particle after particle in the dense solar interior. Once it reaches the surface, it takes only 8 minutes and 20 seconds to cross the 150 million kilometers to Earth. Stars are not merely sources of light. They are engines of chemical enrichment. In their cores, they forge elements heavier than hydrogen and helium. The Sun fuses hydrogen into helium. More massive stars, once they exhaust their hydrogen, contract and heat further, igniting helium fusion to produce carbon and oxygen. Stars above 8 solar masses continue this process, building neon, magnesium, silicon, and finally iron in nested shells like the layers of an onion. Iron is the end of the line for fusion that releases energy. To fuse iron requires more energy than it produces, and so when a massive star develops an iron core, it has reached a terminal state. The collapse that follows is sudden and violent. The iron core, no longer supported by fusion energy, implodes in milliseconds. The outer layers, falling inward at speeds approaching a quarter of the speed of light, bounce off the incompressible core and are expelled in a supernova explosion. For a few weeks, a single dying star can outshine an entire galaxy of 100 billion stars. In that cataclysm, elements heavier than iron are forged. Gold, platinum, uranium, scattered into space to become part of future gas clouds, future stars, future planets. Every atom of iron in your blood was forged in the core of a massive star that died before the Sun was born. Every atom of oxygen you breathe was fused in a stellar interior. Every atom of gold in every ring and circuit was created in the collision of neutron stars or the explosion of supernovae. Stars are not just building blocks of larger structures. They are the factories that produce the periodic table, the sources of nearly every element heavier than hydrogen and helium in the universe. The distribution of stellar masses follows a pattern called the initial mass function. For every star born with 20 times the Sun's mass, there are roughly 1,000 stars born with the Sun's mass, and tens of thousands born with 1/10 the Sun's mass. The universe is dominated by small, dim, long-lived red dwarfs. Proxima Centauri, the nearest star to the Sun at 4.24 light-years, is such a star, a red dwarf with only 12% of the Sun's mass and less than 1% of its luminosity. It will burn for trillions of years, long after the Sun has swelled into a red giant and shed its outer layers into a planetary nebula. Stars do not exist in isolation. They form in clusters, they orbit in pairs and multiples, they gather into galaxies by the hundreds of billions. But before understanding those larger structures, it is essential to understand the star itself, a sphere of plasma held together by gravity, powered by nuclear fusion, radiating energy into space for millions or billions of years. Every galaxy is made of stars. Every cluster, every supercluster, every filament of the cosmic web is ultimately built from these fundamental units of luminous matter. The nearest stars to the Sun form a sparse neighborhood. Within 10 light-years, there are only about a dozen stellar systems. Alpha Centauri, a triple-star system, lies 4.37 light-years away. Barnard's star, a dim red dwarf moving rapidly across the sky, sits at 5.96 light-years. Wolf 359, another red dwarf, is 7.86 light-years distant. These distances are almost incomprehensibly large by human standards. Light itself, traveling at 299,792 kilometers per second, takes years to cross them. The fastest spacecraft ever launched, the Parker Solar Probe, would take thousands of years to reach even the nearest star. And yet, in cosmic terms, these distances are trivially small. The Milky Way galaxy spans 100,000 light-years. The nearest large galaxy, Andromeda, lies 2.5 million light-years away. The observable universe extends 46.5 billion light-years in every direction. Against such scales, the space between neighboring stars is barely a rounding error, but it is in that local space, among individual stars and their gravitational interactions, that the first level of cosmic architecture begins to take shape. Stars rarely exist in isolation. The same gravitational forces that draw hydrogen clouds into collapsing cores also bind stars together in pairs, triplets, and more complex arrangements. When astronomers survey the stellar population of the Milky Way, they find that roughly half of all Sun-like stars have at least one companion. Among the most massive stars, those 10 or 20 times the mass of our Sun, the fraction rises to nearly 90%. Solitary stars like our own are, in a sense, the minority. The physics behind this prevalence is straightforward. When a molecular cloud collapses, it rarely does so uniformly. Turbulent eddies within the gas create regions of varying density. As gravity pulls material inward, these irregularities can fragment the collapsing cloud into two or more distinct cores, each destined to become a separate star. If these cores form close enough together, within a few hundred astronomical units, where 1 astronomical unit equals the distance from Earth to the Sun, about 150 million kilometers. Their mutual gravitational attraction will bind them into a single system. They will orbit a common center of mass for billions of years, locked in an eternal gravitational embrace. The nearest star system to our Sun demonstrates this principle perfectly. Alpha Centauri, lying 4.37 light-years away, is not a single star, but a triple system. Alpha Centauri A and Alpha Centauri B orbit each other at an average distance of about 23 astronomical units, roughly the distance from our Sun to Uranus, completing one orbit every 79.9 years. Their combined mass is approximately 2.1 solar masses. Far beyond them, at a distance of about 13,000 astronomical units, a small red dwarf called Proxima Centauri traces a much longer orbit, taking perhaps 550,000 years to complete a single circuit around its two larger companions. Proxima is the closest star to Earth, yet it is gravitationally bound to a system whose inner pair lies trillions of kilometers away. The orbital mechanics of binary stars follow the same laws that govern planets around the Sun. Johannes Kepler's equations, refined by Isaac Newton's theory of universal gravitation, describe how two masses orbit their common barycenter, the center of mass of the system. If the two stars have equal mass, the barycenter lies exactly midway between them, and both stars trace identical orbits around that point. If one star is significantly more massive, the barycenter shifts toward it, and the lighter companion sweeps through a larger arc. The orbital period depends on the total mass and the separation. Closer, more massive pairs orbit faster, while widely separated pairs take centuries or millennia to complete a single revolution. Sirius, the brightest star in Earth's night sky at a distance of 8.6 light-years, provides another example. Sirius A is a white main-sequence star about twice the mass of the Sun and 25 times more luminous. Its companion, Sirius B, is a white dwarf, the collapsed remnant of a star that exhausted its nuclear fuel long ago. Sirius B packs roughly one solar mass into a sphere the size of Earth, giving it a density of about 1.7 million grams per cubic centimeter. The two stars orbit their common center of mass every 50.1 years, with an average separation of about 20 astronomical units. The existence of Sirius B was predicted mathematically in 1844, when astronomer Friedrich Bessel noticed that Sirius A wobbled slightly in its motion across the sky. The invisible companion was finally observed directly in 1862. This wobble method remains one of the primary techniques for detecting binary systems. Even when a companion star is too faint to see directly, its gravitational influence reveals itself through the motion of the visible star. Spectroscopic binaries take this further. As two stars orbit each other, their light shifts toward blue when approaching Earth and toward red when receding. By measuring these Doppler shifts in stellar spectra, astronomers can determine orbital periods, velocities, and, with geometric information, the masses of both components. The precision of modern spectroscopy allows detection of velocity changes as small as a few meters per second, revealing companions that would otherwise remain invisible. Some binary systems are oriented so that, from Earth's perspective, the two stars periodically pass in front of each other. These eclipsing binaries dim predictably as one star blocks the light of the other. Algol, in the constellation Perseus, was one of the first such systems recognized. Every 2.87 days, Algol's brightness drops by about 1.3 magnitudes as its fainter companion transits across the brighter primary. The regularity of this dimming, noted by ancient astronomers who called it the demon star, arises from the clockwork precision of orbital mechanics. Beyond simple pairs, gravitational binding can create hierarchical systems of considerable complexity. The star system Castor, one of the twin stars of Gemini at 51 light-years distant, contains 6 stars arranged in 3 pairs. Castor A and Castor B are themselves spectroscopic binaries, each consisting of 2 stars orbiting so closely that they cannot be resolved visually. These 2 pairs orbit each other at a distance of about 100 astronomical units, completing 1 revolution every 450 years. A third pair, Castor C, orbits the inner 4 at a much greater distance, taking roughly 14,000 years to complete its circuit. The entire system is gravitationally bound, its 6 stars tracing interlocking paths through space like a cosmic clockwork mechanism. The stability of such hierarchical systems depends on their geometry. For a multiple star system to persist over billions of years, the orbital separations must follow certain ratios. Inner pairs must be compact enough that their mutual gravity dominates over perturbations from outer companions. Outer companions must be distant enough that they do not disrupt the inner orbits. When these conditions are met, the system can remain stable for the entire main sequence lifetime of its stars. When they are not, gravitational interactions can eject members from the system entirely, flinging them into interstellar space as runaway stars. The mass exchange between close binary stars adds another layer of complexity. When 2 stars orbit within a few stellar radii of each other, the more evolved star, swelling as it ages, can overflow its Roche lobe, the teardrop-shaped region where its gravity dominates. Material streams from the bloated star onto its companion, sometimes forming an accretion disk that glows with the heat of infalling gas. In extreme cases, this mass transfer can trigger nova explosions or even Type 1a supernova, when a white dwarf accumulates enough material to exceed the Chandrasekhar limit of 1.4 solar masses and collapses catastrophically. These binary and multiple systems represent the first rung on the ladder of cosmic architecture. Individual stars, bound by gravity into pairs and small groups, demonstrate how mass attracts mass across the vacuum of space. The same force that holds Sirius A and Sirius B in their 50-year dance operates on every scale, from planetary systems to galaxy clusters. But stars can congregate in far larger numbers. When dozens, hundreds, or thousands of stars share a common origin and move together through the galaxy, they form the next level of structure. Stellar clusters, where the gravitational relationships grow more complex and the timescales stretch across hundreds of millions of years. Within the spiral arms of galaxies like our own, where gas and dust concentrate in dense ribbons, stars do not form alone. They emerge in groups, sometimes dozens, sometimes thousands, all born from the same collapsing molecular cloud within a span of just a few million years. These are open clusters, loose, irregularly shaped gatherings of stars that share a common origin, a common motion through space, and a common chemical fingerprint. They represent stellar nurseries caught in the act of dispersing. Families of suns still traveling together before the galaxy eventually pulls them apart. The Pleiades, visible to the naked eye in the constellation Taurus, offers perhaps the most familiar example. At a distance of approximately 444 light-years from Earth, this cluster contains over 1,000 confirmed members, though only 6 or 7 shine brightly enough for unaided human vision to detect. The cluster spans roughly 43 light-years across, and its stars move together through space at about 40 kilometers per second relative to the Sun. Spectroscopic analysis reveals that these stars share nearly identical metallicity, the proportion of elements heavier than hydrogen and helium in their composition, confirming their birth from the same primordial cloud approximately 100 million years ago. The physics governing open clusters differs fundamentally from the tight gravitational binding of binary systems, where a binary pair might orbit with a separation measured in astronomical units or even fractions of an astronomical unit. The stars in an open cluster spread across light years of space. The gravitational potential well holding them together is correspondingly shallow. A typical open cluster might have a total mass between 100 and 1,000 solar masses, creating a gravitational influence that extends perhaps 30 to 50 light-years from the cluster center. Stars within this radius feel a gentle but persistent tug toward the common center of mass, their individual velocities balanced against the collective pull of their siblings. This balance proves delicate. The velocity dispersion within an open cluster, the range of speeds at which individual stars move relative to the cluster's center, typically measures between 1 and 3 kilometers per second. This seems slow compared to the 230 kilometers per second at which the entire cluster orbits the galactic center, but it carries profound implications. Stars moving at the upper end of this velocity range, particularly those near the cluster's outer edges, possess enough kinetic energy to eventually escape the cluster's gravitational embrace entirely. The cluster bleeds members slowly, like a leaky container, losing stars to the surrounding galactic disk over hundreds of millions of years. The Hyades, located roughly 153 light-years from Earth, in the same constellation as the Pleiades, demonstrates this dispersal process at a more advanced stage. At approximately 625 million years old, the Hyades has had 6 times longer than the Pleiades to lose members to the galaxy. Its core contains only about 400 stars spread across 65 light-years, but careful measurements of stellar motions have identified additional former members now scattered across hundreds of light-years of space, still moving in roughly the same direction but no longer gravitationally bound to the main group. These stellar streams represent the ghosts of clusters past, stretched and smeared by differential rotation as the inner and outer portions of their galactic orbits proceed at different rates. The process of cluster dissolution follows predictable dynamics rooted in gravitational physics. As a cluster orbits the galactic center, it experiences tidal forces, the same phenomenon that raises ocean tides on Earth, but operating across vastly larger scales. The side of the cluster closer to the galactic center feels a slightly stronger gravitational pull than the far side. This differential stretches the cluster along the direction of its orbit, creating elongated tidal tails of escaping stars. Simultaneously, encounters with giant molecular clouds, those same dense regions of gas that birth new clusters, can inject energy into the cluster's stellar population, accelerating the escape of marginal members. The timescale for complete dissolution depends on the cluster's initial mass and its orbital path through the galaxy. A sparse cluster of 100 stars might disperse entirely within 100 million years. A richer cluster of several thousand stars could persist for 1 billion years or more. The oldest known open clusters, like Berkeley 17 at approximately 10 billion years, survive only because their orbits carry them far from the galactic plane, away from the disruptive influences of molecular clouds and the densest stellar populations. Most open clusters, however, dissolve long before reaching such ages, their members absorbed into the general stellar population of the galactic disk. Messier 67, located about 2,700 light-years away in the constellation Cancer, provides astronomers with a particularly valuable laboratory for studying stellar evolution within a cluster context. At roughly 4 billion years old, nearly the same age as our Sun, M67 contains approximately 500 stars spanning a wide range of masses. The most massive members have long since exhausted their hydrogen fuel and evolved into red giants or white dwarfs. The least massive continue fusing hydrogen in their cores, their lifespans measured in tens of billions of years. By studying stars of known age and identical initial composition, astronomers can test theories of stellar structure and evolution with precision impossible for isolated field stars of uncertain origin. The color magnitude diagram of an open cluster tells the story of stellar aging with remarkable clarity. When astronomers plot the brightness of cluster members against their color, a proxy for surface temperature, the resulting pattern reveals the cluster's age as surely as tree rings reveal the age of an oak. Young clusters show a continuous sequence of stars from hot blue giants to cool red dwarfs, all still burning hydrogen in their cores. As the cluster ages, the most massive and luminous stars exhaust their fuel first, peeling away from the main sequence and evolving toward the red giant branch. The point where this turnoff occurs moves progressively down the sequence as the cluster ages, providing a cosmic clock readable across billions of years. The chemical homogeneity of open clusters makes them essential calibrators for understanding stellar abundances throughout the galaxy. Stars born from the same cloud inherit the same proportions of iron, oxygen, carbon, and dozens of other elements forged in previous generations of stellar nucleosynthesis. When astronomers measure slight variations in these abundances among cluster members, they probe the physics of stellar atmospheres, convective mixing, and atomic diffusion rather than primordial differences. The Hyades, with its well-determined distance and age, serves as a fundamental benchmark for the cosmic distance ladder, its stars providing reference points against which more distant objects can be measured. Open clusters also trace the spiral structure of the Milky Way itself, because they form in the gas-rich spiral arms and disperse relatively quickly. Their distribution maps the current locations of these density waves. Young clusters, less than 50 million years old, concentrate tightly along the arms. Older clusters spread more broadly, their orbits carrying them away from their birthplaces as the spiral pattern rotates through the galactic disk at a different rate than the stars themselves. The Perseus arm, the Sagittarius arm, and our own local arm all reveal themselves through the spatial distribution of their associated open clusters. Within the Milky Way, astronomers have catalogued over 1,100 open clusters, with estimates suggesting several thousand more remain hidden behind obscuring dust clouds or lost in the crowded stellar fields toward the galactic center. Each represents a snapshot of star formation, a cohort of siblings destined to eventually go their separate ways. The Sun itself likely formed in such a cluster approximately 4.6 billion years ago, its birth companions now scattered across thousands of light-years of galactic space, their common origin detectable only through painstaking analysis of chemical abundances and orbital dynamics. Yet open clusters, for all their scientific value, represent merely a transitional form of stellar congregation. Their loose binding and inevitable dissolution contrast sharply with another class of stellar grouping, one far older, far denser, and far more gravitationally robust. In the halos surrounding spiral galaxies, orbiting at distances of tens of thousands of light-years from the galactic plane, exist spherical swarms of hundreds of thousands of stars packed into regions just 100 light-years across. These globular clusters have survived for nearly the entire history of the universe, their stars bound so tightly that escape becomes nearly impossible, their ancient light carrying information about conditions in the cosmos when galaxies themselves were still young. The globular clusters that orbit the Milky Way represent some of the oldest gravitationally bound structures in the observable universe. While open clusters measure their ages in tens or hundreds of millions of years, globular clusters have persisted for 12 to 13 billion years, their formation occurring when the universe itself was less than 1 billion years old. These ancient spheres of stars predate the galactic disk they now orbit, their existence a relic of conditions that prevailed when the first large-scale structures were assembling from the primordial distribution of matter. The Milky Way hosts approximately 150 known globular clusters, though the total number may exceed 200 when accounting for those obscured by dust in the galactic plane. Each cluster contains between 100,000 and several million stars packed into a roughly spherical volume, typically spanning 80 to 200 light-years in diameter. The stellar density at the core of a globular cluster can exceed 1,000 stars per cubic parsec, compared to the solar neighborhood's density of roughly 0.14 stars per cubic parsec. In the innermost regions of the densest clusters, stars may be separated by only a fraction of a light-year, close enough that gravitational interactions between individual stars become significant over timescales of millions of years. Omega Centauri, the largest globular cluster orbiting the Milky Way, contains approximately 10 million stars within a diameter of roughly 150 light-years. Located some 15,800 light-years from Earth, it appears to the naked eye as a fuzzy star in the southern constellation Centaurus. Its mass approaches 4 million solar masses, making it more massive than many dwarf galaxies. Some astronomers suspect Omega Centauri may actually be the stripped core of a small galaxy that was captured and disrupted by the Milky Way's gravity billions of years ago, its outer stars torn away, while its dense nucleus remained intact. The physics governing globular cluster structure involves a delicate balance between gravitational attraction pulling stars inward and the kinetic energy of stellar motions providing outward pressure. This state, known as virial equilibrium, allows the cluster to maintain a stable configuration over billions of years. The virial theorem states that for a gravitationally bound system in equilibrium, the total kinetic energy of the constituent bodies equals -1/2 the gravitational potential energy. When a cluster satisfies this condition, it neither collapses nor expands, but maintains its characteristic spherical shape indefinitely, barring external perturbations. The density profile of a typical globular cluster follows a distinctive pattern. The core region, spanning perhaps a few light years, contains the highest concentration of stars. Moving outward, the density decreases gradually through an intermediate zone before dropping more steeply in the outer halo. This structure can be mathematically described by models such as the King profile, which accounts for the finite extent of clusters by incorporating a tidal radius beyond which stars become unbound due to the gravitational influence of the parent galaxy. For a cluster like 47 Tucanae, located 16,700 light-years away, the core radius measures roughly 24 light-years, while the tidal radius extends to nearly 200 light-years. The stars within globular clusters share remarkably uniform properties. Spectroscopic analysis reveals that stars in a given cluster possess nearly identical chemical compositions, with heavy element abundances typically ranging from 1% to 30% of solar values. This metal poverty indicates formation from gas that had experienced minimal enrichment by previous generations of stellar nucleosynthesis. The uniformity suggests that all stars in a cluster formed from the same molecular cloud during a relatively brief episode of star formation, perhaps spanning only a few million years. Once the most massive stars exhausted their fuel and exploded as supernovae, their winds and blast waves expelled the remaining gas, halting further star formation and freezing the cluster's stellar population in time. Color magnitude diagrams of globular clusters provide powerful tools for determining stellar ages. Because all stars in a cluster formed simultaneously from material of identical composition, they differ primarily in their initial masses. More massive stars evolve faster, exhausting their core hydrogen and leaving the main sequence to become red giants. The main sequence turn-off point, where stars begin departing the main sequence, shifts to progressively lower masses and luminosities as a cluster ages. For ancient globular clusters, only stars with masses below roughly 0.8 solar masses remain on the main sequence, their slow hydrogen burning allowing them to persist for longer than the current age of the universe. By comparing observed turn-off points with theoretical stellar evolution models, astronomers determine ages clustering tightly around 12 to 13 billion years for the oldest globular clusters. The spatial distribution of globular clusters around the Milky Way reveals important information about galactic structure and history. Unlike the disk stars that orbit in the galactic plane, globular clusters occupy a roughly spherical halo extending to distances exceeding 100,000 light-years from the galactic center. Their orbits are highly elliptical and randomly oriented, carrying them through the disk and back out into the halo over periods of hundreds of millions of years. This distribution suggests that globular clusters formed before the gas that would become the galactic disk had settled into its flattened configuration, preserving in their orbits the memory of the galaxy's early, more chaotic state. The formation of globular clusters remains an active area of research. The extreme stellar densities and uniform compositions suggest formation in environments very different from present-day molecular clouds. One hypothesis proposes that globular clusters formed within small, dark matter halos in the early universe, where gas could accumulate and cool efficiently. As these halos merged into larger structures that eventually became galaxies, their globular clusters were incorporated into the growing galactic halos. Another scenario suggests formation during major galaxy mergers, when colliding gas clouds were compressed to the extraordinary densities required to produce such compact stellar systems. Within the cores of the densest globular clusters, stellar dynamics produce exotic objects rarely found elsewhere. The high stellar density leads to frequent close encounters between stars, sometimes resulting in direct collisions that merge two stars into a single, more massive object. These collision products, called blue stragglers, appear anomalously hot and luminous for their cluster's age, as if they were younger than their siblings. Binary star systems in dense cores undergo complex interactions, sometimes exchanging partners or ejecting members entirely. X-ray observations have revealed numerous binary systems containing neutron stars or white dwarfs, actively accreting matter from companion stars, their high-energy emissions betraying the presence of stellar corpses in these ancient stellar cities. The gravitational environment within globular clusters also favors the formation of millisecond pulsars, rapidly spinning neutron stars that have been spun up by accretion from binary companions. The globular cluster Terzan 5, located roughly 19,000 light-years away toward the galactic center, contains at least 37 known millisecond pulsars, more than any other globular cluster. These objects spin hundreds of times per second, their lighthouse beams of radio emission sweeping across Earth with extraordinary regularity. The abundance of millisecond pulsars in globular clusters reflects the high probability of neutron stars acquiring and interacting with binary companions in such crowded environments. Deep in the cores of some globular clusters, evidence suggests the presence of intermediate mass black holes, objects with masses between 100 and 100,000 solar masses. Such black holes would occupy the mass range between stellar mass black holes, formed from individual massive stars, and the supermassive black holes found at galactic centers. The globular cluster Omega Centauri shows kinematic signatures consistent with a central black hole of approximately 40,000 solar masses. Though alternative explanations involving concentrated populations of stellar mass remnants remain viable. If confirmed, such intermediate mass black holes might represent seeds from which supermassive black holes grew through accretion and mergers over cosmic time. The structures that house these ancient stellar spheres extend far beyond what visible light reveals. A galaxy like the Milky Way presents itself to optical telescopes as a flattened disk of stars, gas, and dust. But this luminous component represents merely a fraction of the total gravitational system. Understanding a galaxy requires examining its complete architecture, from the dense central regions where stars crowd together by the millions to the vast invisible envelope that extends hundreds of thousands of light-years into surrounding space. The disk of a spiral galaxy constitutes its most recognizable feature. In the Milky Way, this disk spans approximately 100,000 light-years in diameter, but maintains a thickness of only about 1,000 light-years through most of its extent. This extreme flattening results from the physics of angular momentum conservation. As the primordial gas cloud that formed the galaxy collapsed under gravity, any initial rotation became amplified. Material falling inward while conserving angular momentum naturally settles into a rotating disk, much as water spiraling down a drain flattens into a thin sheet. The disk contains the youngest stellar populations, ongoing star formation, and the spiral arms that give these galaxies their classification. Within the disk, density waves propagate through the stellar and gaseous material, creating the spiral pattern visible in countless Hubble images. These waves move through the disk at speeds different from the orbital velocities of individual stars, typically around 200 to 300 kilometers per second relative to the rotating material. As gas clouds encounter these density waves, compression triggers gravitational collapse and star formation. The bright blue stars that trace spiral arms are not permanent residents of those structures, but rather short-lived markers of recent compression events. A massive blue star born in a spiral arm will exhaust its nuclear fuel and explode as a supernova within 10 million years, long before it completes even a single orbit around the galactic center. The spiral pattern persists, not because the same stars remain within it, but because the density wave continuously triggers new star formation as it sweeps through the disk. The central bulge presents a markedly different stellar environment. This roughly spherical concentration of stars extends several thousand light-years from the galactic center and contains stellar populations significantly older than those in the disk. In the Milky Way, the bulge harbors stars with ages exceeding 10 billion years, formed during the earliest epochs of the galaxy's assembly. The stellar density in the bulge exceeds that of the disk by factors of hundreds or thousands. Near the galactic center, stars crowd together with separations measured in light weeks rather than light years. If Earth orbited a star in the central bulge, the night sky would blaze with thousands of stars bright enough to cast shadows, a perpetual twilight of stellar illumination. The bulge formed through different mechanisms than the disk. During the chaotic early assembly of the galaxy, smaller protogalactic fragments merged and their stars scattered onto randomly oriented orbits. This violent relaxation process erased the organized rotation that characterizes disk formation, leaving instead a pressure-supported structure where stellar motions point in all directions. Some bulges show evidence of more recent formation through disk instabilities, where gravitational interactions cause disk material to flow inward and pile up in the central regions. The Milky Way's bulge displays a distinctly boxy or peanut-shaped morphology when viewed from certain angles, suggesting it formed at least partially through such instability processes rather than purely through early mergers. At the precise center of the bulge lies the supermassive black hole. In the Milky Way, this object carries the designation Sagittarius A star and possesses a mass of approximately 4 million solar masses compressed into a region smaller than the orbit of Mercury. Despite containing the mass of 4 million suns, Sagittarius A star occupies a volume so small that its event horizon spans only about 24 million kilometers, roughly 17 times the diameter of the Sun. The gravitational influence of this black hole dominates stellar motions within the central few light-years. Stars in this region orbit at velocities exceeding 1,000 kilometers per second, completing full orbits in as little as 16 years. The star designated S2 approaches within 120 astronomical units of the black hole at closest approach, experiencing gravitational time dilation and relativistic effects directly measurable from Earth. Supermassive black holes appear to be universal features of massive galaxies. Observations across hundreds of galaxies reveal a tight correlation between black hole mass and the properties of the surrounding bulge. Black holes typically contain approximately 0.1% of the bulge's stellar mass, a ratio that holds across galaxies spanning orders of magnitude in size. This correlation implies a co-evolution between black holes and their host galaxies, though the physical mechanisms enforcing this relationship remain subjects of active research. During episodes of rapid accretion, supermassive black holes power active galactic nuclei that can outshine their entire host galaxy by factors of hundreds. The energy released during such episodes may regulate star formation throughout the galaxy, heating and expelling gas that would otherwise collapse into new stars. Beyond the visible disk and bulge extends the galactic halo, a roughly spherical distribution of old stars, globular clusters, and most significantly, dark matter. The stellar halo of the Milky Way contains only about 1 billion stars, less than 1% of the disk population. But these stars trace orbits extending more than 100,000 light-years from the galactic center. Many halo stars travel on highly elliptical paths that plunge through the disk before swinging back out into the sparse outer regions. The chemical compositions of halo stars reveal their ancient origins, with iron abundances sometimes less than 1,000th that of the Sun, indicating formation before multiple generations of supernovae had enriched the interstellar medium with heavy elements. The dark matter halo dwarfs all luminous components combined. Extending perhaps 300,000 light-years from the galactic center, this invisible structure contains approximately 1 trillion solar masses of matter that interacts gravitationally but neither emits nor absorbs light. The evidence for this dark matter comes from multiple independent observations. Stars in the outer disk orbit at velocities around 220 kilometers per second, speeds that would fling them into intergalactic space if only the visible matter provided gravitational attraction. The rotation curve of the galaxy, plotting orbital velocity against distance from the center, remains flat or even rises slightly at large radii rather than declining as expected for a centrally concentrated mass distribution. This flat rotation curve requires additional mass distributed in an extended halo, mass that optical and radio telescopes cannot detect. The dark matter halo likely formed first, providing the gravitational potential well into which ordinary matter subsequently fell. Simulations of cosmic structure formation show dark matter collapsing into halos, while ordinary matter, still coupled to radiation in the early universe, remained smoothly distributed. Only after the universe cooled sufficiently for atoms to form could ordinary matter begin falling into these pre-existing dark matter structures. The gas that would eventually form stars first accumulated at the centers of dark matter halos, cooling through radiation and condensing into the disks and bulges we observe today. In this picture, galaxies are not isolated islands of stars, but rather the luminous cores of much larger dark matter structures, visible traces of an underlying gravitational architecture that extends far beyond what any telescope can image. These luminous cores, these visible traces of dark matter's invisible architecture, present themselves to observers in a remarkable variety of forms. When astronomers began systematically cataloguing galaxies in the early 20th century, they discovered that these vast stellar systems fall into distinct morphological categories, each reflecting different histories of formation, merger, and evolution. The classification scheme developed by Edwin Hubble in 1926, though refined and expanded over subsequent decades, still provides the foundation for understanding how mass distributes itself across the galaxy population of the observable universe. Spiral galaxies like our own Milky Way represent perhaps the most visually striking category. These systems feature prominent disk structures where stars, gas, and dust orbit the galactic center in roughly circular paths. The disk of a typical spiral extends between 50,000 and 200,000 light-years in diameter, with thicknesses measuring only a few thousand light-years. This extreme flattening results from the conservation of angular momentum during collapse. As the original gas cloud contracted under gravity, any initial rotation became amplified, spinning the material into a flattened configuration, much as pizza dough spreads when tossed. Within these disks, density waves propagate outward from the center, compressing gas and triggering star formation along spiral arms that wind through the stellar population. The Milky Way possesses 4 major spiral arms, with our solar system located in a minor spur called the Orion Arm, approximately 26,000 light-years from the galactic center. The mass distribution within spiral galaxies reveals the dominance of dark matter at large radii. Observations of stellar and gas velocities show that material at the outer edges of spiral disks orbits at speeds between 200 and 300 kilometers per second, roughly the same velocity as material much closer to the center. This flat rotation curve contradicts what visible matter alone would predict. If only stars and gas contributed to the gravitational potential, orbital velocities should decline with distance from the center, following Keplerian dynamics like planets orbiting the Sun. The persistence of high velocities at large radii implies the presence of additional mass extending far beyond the visible disk. For the Milky Way, this dark matter halo contains approximately 1 trillion solar masses, roughly 10 times the mass of all visible stars combined, and extends to a radius of perhaps 300,000 light-years. Elliptical galaxies present a strikingly different morphology. These systems lack the organized disk structure of spirals, instead displaying smooth, roughly spheroidal distributions of stars. The smallest ellipticals, classified as dwarf ellipticals, contain only a few million stars and span perhaps 3,000 light-years. The largest designated giant ellipticals, or CD galaxies, rank among the most massive stellar systems known. IC 1101, located at the center of the Abell 2029 galaxy cluster, approximately 1 billion light-years distant, extends across 6 million light-years and contains an estimated 100 trillion stars. Its total mass, including dark matter, approaches 100 trillion solar masses, making it thousands of times more massive than the Milky Way. The stellar populations within elliptical galaxies differ fundamentally from those in spirals. Ellipticals contain predominantly old red stars with ages exceeding 10 billion years. Star formation in these systems largely ceased billions of years ago, leaving behind aging stellar populations that slowly fade as their most massive members exhaust their nuclear fuel. The absence of significant gas and dust explains this quiescence. While spiral galaxies maintain gas reservoirs that continuously fuel new star formation, ellipticals have either consumed their gas in ancient starbursts or lost it through various processes, including ram pressure stripping when moving through hot intracluster medium. The formation of elliptical galaxies connects intimately to the merger history of the universe. Simulations and observations both suggest that major mergers between spiral galaxies can produce elliptical remnants. When two disk galaxies of comparable mass collide, their organized rotational motion becomes scrambled through gravitational interactions. Stars that once followed nearly circular orbits find themselves on chaotic, randomly oriented trajectories. The resulting system loses the flattened disk structure and settles into a more spheroidal configuration supported by the random motions of its stars rather than organized rotation. This process, called violent relaxation, occurs over timescales of a few 100 million years. The giant ellipticals found at the centers of galaxy clusters have likely experienced multiple such mergers, growing through the successive accumulation of smaller systems over cosmic time. Lenticular galaxies occupy an intermediate position between spirals and ellipticals. These systems possess disk structures like spirals, but lack prominent spiral arms and contain little gas for ongoing star formation. They appear as smooth disks with central bulges, representing perhaps a transitional stage in galaxy evolution. A spiral galaxy that exhausts or loses its gas supply might evolve into a lenticular configuration, retaining its disk structure while ceasing to form new stars. The fraction of lenticular galaxies increases dramatically in dense cluster environments, suggesting that environmental processes play a role in their formation. Irregular galaxies defy the neat categorization of spirals and ellipticals. These systems display chaotic, asymmetric structures, often resulting from gravitational interactions or mergers. the Large and Small Magellanic Clouds, satellite galaxies of the Milky Way located approximately 160,000 and 200,000 light-years distant respectively, exemplify this category. The Large Magellanic Cloud contains roughly 30 billion solar masses and spans 14,000 light-years, while its smaller companion holds approximately 7 billion solar masses. Both show evidence of tidal distortion from their gravitational interaction with the Milky Way and with each other. The distribution of galaxy types varies systematically with environment. In the low-density field regions between galaxy clusters, spirals dominate the population, comprising roughly 70% of bright galaxies. In the dense cores of galaxy clusters, this ratio inverts, with ellipticals and lenticulars accounting for the majority. This morphology-density relation reflects the influence of environment on galaxy evolution. Cluster galaxies experience processes absent in isolation, including gravitational harassment from repeated high-speed encounters, ram pressure stripping of gas by the hot intracluster medium, and an increased probability of mergers during the cluster assembly process. The total stellar mass contained in galaxies across the observable universe amounts to approximately 100 billion trillion solar masses, distributed among roughly 2 trillion galaxies. This stellar mass represents only about 5% of the total matter content, with dark matter comprising the remaining 95% of gravitating material. The most massive galaxies, the giant ellipticals at cluster centers, contain stellar masses approaching 10 trillion solar masses, while the smallest dwarf galaxies hold only a few 100,000 solar masses in stars. This mass distribution follows a characteristic function, with low-mass galaxies vastly outnumbering their giant counterparts. For every galaxy as massive as the Milky Way, hundreds of dwarf galaxies populate the universe, though their faintness makes them difficult to detect at large distances. The faintness of these dwarf galaxies points toward something far more significant than mere observational difficulty. Their very existence, their ability to hold together as coherent structures despite containing so few stars, reveals the presence of matter that emits no light, absorbs no radiation, and interacts with ordinary matter only through the patient pull of gravity. This dark matter, comprising approximately 85% of all matter in the universe, forms the invisible scaffolding upon which every galaxy, from the smallest dwarf spheroidal to the most massive giant elliptical, has been constructed. The evidence for dark matter halos emerged gradually through the 20th century, accumulating from observations that simply could not be explained by visible matter alone. In the 1930s, the astronomer Fritz Zwicky studied the Coma cluster, measuring the velocities of its member galaxies as they orbited within the cluster's gravitational embrace. The galaxies moved far too quickly. Based on the visible mass alone, the cluster should have flown apart billions of years ago, its galaxies scattering into the void like leaves released from a dying tree. Yet the cluster remained bound, held together by matter that Zwicky could not see, but whose gravitational influence he could measure. He calculated that the cluster must contain at least 400 times more mass than the visible galaxies suggested, a ratio that subsequent observations have refined but fundamentally confirmed. 4 decades later, the astronomer Vera Rubin provided equally compelling evidence at the scale of individual galaxies. She measured the rotation curves of spiral galaxies, tracking how quickly stars and gas clouds orbit at various distances from the galactic center. In a system dominated by visible matter, orbital velocities should decrease with distance from the center, following the same pattern that governs planets in our solar system. Mercury orbits the Sun at 47 kilometers per second, while Neptune, 30 times more distant, crawls along at only 5 kilometers per second. The mass concentrates at the center, and objects farther out feel weaker gravitational pull. Spiral galaxies refused to follow this pattern. Rubin found that rotation curves remained essentially flat, with stars at the outer edges of galaxies orbiting just as quickly as those closer to the center. In the Andromeda Galaxy, stars 50,000 light-years from the center orbit at approximately 230 kilometers per second. Stars 100,000 light-years out move at nearly the same speed. This flat rotation curve implies that mass continues to accumulate even in regions where visible matter has become sparse, as though each galaxy sits embedded within an enormous sphere of invisible material that extends far beyond the visible disk. Modern observations have mapped these dark matter halos with increasing precision. The halo surrounding the Milky Way extends to approximately 1 million light-years from the galactic center, roughly 10 times the diameter of the visible disk. Its total mass amounts to approximately 1 to 2 trillion solar masses, of which visible stars, gas, and dust contribute only about 200 billion solar masses. The dark matter outweighs the ordinary matter by a factor of 5 to 10, depending on how far out one measures. This ratio holds across galaxies of all types and sizes, suggesting that dark matter halos represent a universal feature of galaxy architecture rather than a peculiarity of certain systems. The density profile of these halos follows a characteristic pattern first described by the physicists Julio Navarro, Carlos Frenk, and Simon White in 1996. The NFW profile, as it has come to be known, describes a density that increases toward the center, but never reaches a sharp peak, instead forming a cusp where density rises steeply but remains finite. At large radii, the density falls off proportionally to the inverse cube of the distance, meaning that doubling the distance from the center reduces the density by a factor of 8. This profile emerges naturally from computer simulations of dark matter clustering, where particles interact only through gravity and gradually settle into configurations that balance their random motions against gravitational attraction. The formation of these halos preceded the formation of galaxies themselves. In the early universe, approximately 400,000 years after the Big Bang, matter existed as a nearly uniform sea of particles, with density variations of only 1 part in 100,000. These tiny fluctuations, imprinted during the first moments of cosmic inflation, provided the seeds from which all structure would eventually grow. Dark matter, unimpeded by interactions with radiation, began collapsing into these overdense regions immediately, while ordinary matter remained coupled to the cosmic background radiation and could not yet fall inward. By the time the universe reached an age of approximately 1 billion years, dark matter had assembled into halos spanning a wide range of masses. The smallest halos, containing perhaps 1 million solar masses of dark matter, formed first, their higher densities allowing gravity to overcome cosmic expansion more quickly. These small halos then merged hierarchically, combining into progressively larger structures through a process that continues to the present day. The Milky Way's halo represents the accumulated merger of thousands of smaller halos over 13 billion years, each collision adding mass and reshaping the overall structure. Ordinary matter followed dark matter into these gravitational wells, but its journey proved more complex. Unlike dark matter, which interacts only through gravity, ordinary matter can collide, radiate energy, and lose angular momentum. Gas falling into a dark matter halo initially heats through compression, reaching temperatures of millions of degrees in the most massive halos. This hot gas then radiates energy away, primarily through X-ray emission, and gradually cools toward the center of the halo. As it cools, it loses pressure support and continues falling inward, eventually settling into a rotating disk where densities become high enough to trigger star formation. The efficiency of this cooling process depends critically on the mass of the dark matter halo. In halos below approximately 10 billion solar masses, the gravitational potential remains too shallow to heat infalling gas to temperatures where it can cool efficiently. The gas enters the halo cold and may form stars in irregular bursts, producing the dwarf galaxies that populate the outskirts of larger systems. In halos above approximately 1 trillion solar masses, the gas heats to such extreme temperatures that cooling times exceed the age of the universe. This hot gas remains suspended in the halo, unable to collapse and form stars, explaining why the most massive dark matter halos often host elliptical galaxies with little ongoing star formation. The Milky Way's halo falls within the intermediate range, where cooling operates most efficiently. Gas has been able to settle into a well-defined disk, maintain ongoing star formation for over 10 billion years, and build up the spiral structure visible today. The halo continues to accrete new material from the intergalactic medium, with approximately 1 solar mass of fresh gas falling onto the disk each year, roughly balancing the rate at which gas converts into new stars. Within this dark matter halo, smaller structures persist as remnants of the hierarchical assembly process. Computer simulations predict that a Milky Way mass halo should contain hundreds of smaller subhalos, each representing a dark matter clump that fell in but was not completely disrupted by tidal forces. Some of these subhalos host the dwarf satellite galaxies that orbit the Milky Way, their visible stars tracing only the densest central regions of much larger dark matter structures. The Draco dwarf spheroidal galaxy, for instance, contains only about 300,000 solar masses in stars, but sits within a dark matter subhalo of approximately 100 million solar masses. Its stars move with velocities that would tear the system apart in the absence of this invisible gravitational binding. The Draco dwarf spheroidal represents just one member of an extensive family of satellite galaxies that orbit within the Milky Way's gravitational sphere of influence. At least 60 such companions have been identified, ranging from the substantial Large Magellanic Cloud down to ultra-faint dwarfs containing fewer stars than some globular clusters. This hierarchy of gravitational capture reflects the fundamental process by which large structures, grow in a universe dominated by dark matter. Smaller halos fall into larger ones, some merging completely, others surviving as distinct satellites orbiting within their host's extended halo. The Large Magellanic Cloud, visible to the naked eye from the southern hemisphere, contains approximately 10 billion solar masses in stars and orbits the Milky Way at a distance of roughly 160,000 light-years. Its irregular shape and active star formation distinguish it from the quiescent dwarf spheroidals that populate the outer halo. The Large Magellanic Cloud is massive enough to retain its own gas supply, fueling ongoing stellar birth at a rate of approximately 0.2 solar masses per year. Its companion, the Small Magellanic Cloud, follows a similar orbit at about 200,000 light-years, containing perhaps 7 billion solar masses in total. Together, these two galaxies are falling toward the Milky Way for what may be their first close passage, their mutual gravitational interaction drawing out a bridge of gas and stars known as the Magellanic Stream that stretches across more than 100 degrees of the sky. The dynamics of satellite capture reveal themselves through careful measurement of orbital velocities and trajectories. The Sagittarius Dwarf Elliptical Galaxy, discovered in 1994, provides a dramatic example of a satellite in the final stages of gravitational disruption. Located only 70,000 light-years from the galactic center, Sagittarius has passed through the Milky Way's disk multiple times over the past several billion years. Each passage strips away stars through tidal forces, leaving behind streams of stellar debris that wrap around the entire galaxy. These tidal streams have been traced across the sky, forming great circles that record the orbital history of the doomed satellite. The main body of Sagittarius retains perhaps 400 million solar masses, but the streams contain comparable mass, material that once belonged to the dwarf, but now traces independent orbits through the Milky Way's halo. The physics of tidal disruption operates through differential gravitational forces. Stars on the near side of a satellite experience stronger attraction toward the host galaxy than stars on the far side. This gradient in gravitational pull stretches the satellite along its orbital path, eventually exceeding the satellite's own self-gravity and pulling stars free. The rate of disruption depends on the satellite's orbital pericenter, its closest approach to the host, and on the density of the satellite itself. Compact satellites with high central densities survive longer than diffuse ones. The ultra-compact dwarf galaxies, with half-light radii of only 20 to 50 parsecs, represent the most resilient structures, their tight gravitational binding allowing them to resist tidal forces that would shred more extended systems. The distribution of satellite galaxies around the Milky Way presents puzzles that continue to challenge theoretical models. Rather than orbiting in random orientations as simple hierarchical clustering might predict, many of the Milky Way's satellites appear to lie within a thin plane, the so-called vast polar structure, inclined roughly perpendicular to the galactic disk. This planar arrangement extends across more than 1 million light-years and includes about half of the known classical satellites. A similar structure exists around Andromeda, where approximately 15 satellites orbit within a thin rotating plane. Whether these configurations arise from group infall where multiple satellites entered together along a cosmic filament, or from some other dynamical process, remains an active area of research. The missing satellite problem once posed a significant challenge to the cold, dark matter paradigm. Simulations predicted that a Milky Way mass halo should contain thousands of subhalos, massive enough to host visible galaxies, yet only dozens of satellites were known. This discrepancy has largely been resolved through improved understanding of how baryonic physics suppresses star formation in small halos. Ultraviolet radiation from the first stars and galaxies heated intergalactic gas, preventing it from falling into halos with virial temperatures below about 10,000 Kelvin. This process, called reionization, effectively sterilized halos below roughly 1 billion solar masses, leaving them dark. The subhalos exist, but most contain no stars, remaining invisible except through their gravitational effects. The discovery of ultrafaint dwarf galaxies beginning in 2005 has partially bridged the gap between predictions and observations. These systems, with luminosities as low as a few hundred solar luminosities, represent the faintest galaxies known. Segue 1, one of the most extreme examples, contains only about 1,000 stars spread across a region roughly 50 parsecs in diameter. Its velocity dispersion of approximately 3.7 kilometers per second implies a mass-to-light ratio exceeding 1,000, making it one of the most dark matter-dominated objects ever measured. The stars in Segue 1 are ancient, with ages exceeding 12 billion years and metallicities below 1% of solar, indicating that star formation ceased very early, likely quenched by reionization. The satellite population of the Milky Way thus preserves a fossil record of structure formation in the early universe. The most massive satellites, like the Magellanic Clouds, fell thin recently and retain gas and ongoing star formation. Intermediate mass satellites like Fornax and Sculptor lost their gas billions of years ago, but retain extended stellar populations built up over several billion years of star formation. The ultrafaint dwarfs represent the most ancient and primitive systems. Their star formation truncated almost immediately after the first generation of stars formed. Together, these satellites span a factor of 100 million in luminosity and trace the full hierarchy of gravitational capture that has built the Milky Way's halo over cosmic time. This hierarchy of gravitational capture extends beyond the Milky Way itself, connecting our galaxy to dozens of neighbors in a structure astronomers call the local group. The term sounds modest, almost provincial, yet this assemblage of galaxies spans roughly 10 million light-years and contains more than 80 known members bound together by their mutual gravitational attraction. The local group represents the smallest scale at which galaxies themselves become the building blocks of larger structures, the first rung on a ladder that will eventually climb to formations spanning hundreds of millions of light-years. The gravitational architecture of the local group centers on two dominant masses. The Milky Way, with its trillion solar masses of combined baryonic and dark matter, anchors one end of this structure. The Andromeda Galaxy, also catalogued as Messier 31, commands the other end with a total mass that recent measurements place between 1.2 and 2 trillion solar masses. These two spiral galaxies account for approximately 90% of the local group's total mass, with everything else, the dozens of dwarf galaxies, the irregular satellites, the scattered globular clusters, representing gravitational subordinates orbiting within the combined potential well of these twin giants. The distance separating the Milky Way and Andromeda measures approximately 2.5 million light-years, a span that light requires 2.5 million years to cross. Yet this separation is not static. Spectroscopic measurements of Andromeda's light reveal a blue shift corresponding to an approach velocity of roughly 110 kilometers per second. While the universe as a whole expands, carrying distant galaxies away from us at ever-increasing speeds, Andromeda moves toward us, its gravitational attraction to the Milky Way overwhelming the cosmic expansion at this relatively close range. The two galaxies have been falling toward each other since the universe was young, their mutual gravity drawing them into an inevitable collision that will unfold approximately 4.5 billion years from now. This approaching merger illustrates a fundamental principle governing structures at this scale. Galaxy groups represent gravitationally bound systems, meaning the escape velocity required to leave the group exceeds the velocities imparted by cosmic expansion. Within the local group's boundaries, gravity wins. Beyond those boundaries, expansion dominates, and neighboring groups recede from us at speeds proportional to their distance. The local group thus exists as an island of gravitational coherence in an expanding universe, its members destined to interact, merge, and eventually coalesce into a single, massive structure over timescales measured in tens of billions of years. Between the two dominant spirals lies a third significant galaxy, though far smaller than either giant. The Triangulum galaxy, Messier 33, contains roughly 40 billion stars and orbits at a distance of approximately 2.7 million light-years from the Milky Way. Its total mass, including its dark matter halo, reaches perhaps 50 billion solar masses, substantial by most standards, yet only a few percent of either dominant spiral's mass. Triangulum's relationship to Andromeda remains a subject of ongoing investigation. Some measurements suggest it may be a satellite of Andromeda, gravitationally bound to the larger spiral and destined to merge with it before the eventual Milky Way collision. Other analyses indicate Triangulum may be on its first approach to Andromeda, not yet captured into a bound orbit. The remaining members of the local group fall into the category of dwarf galaxies, ranging from the relatively massive Magellanic Clouds down to ultra-faint systems containing only a few thousand stars. These dwarfs distribute themselves unevenly across the group's volume. The Milky Way claims at least 60 satellites within its virial radius. Andromeda hosts a comparable or larger population, with confirmed satellites including Messier 32, a compact elliptical galaxy containing roughly 3 billion stars, and NGC 205, a dwarf elliptical with approximately 300 million stars. Both orbit within 200,000 light-years of Andromeda's center, close enough that tidal forces from the larger galaxy have likely stripped material from their outer regions. The spatial distribution of these dwarf satellites reveals patterns that challenge simple theoretical predictions. Around both the Milky Way and Andromeda, many satellite galaxies align in thin planar structures, rather than distributing themselves spherically, as dark matter simulations might suggest. The Milky Way's satellites show a pronounced concentration toward a plane roughly perpendicular to the galactic disk, a structure sometimes called the vast polar structure. Andromeda's satellites display an even more striking alignment, with approximately half orbiting within a thin plane only 50,000 light-years thick, yet extending over 1,000,000 light-years in diameter. Whether these planar distributions result from satellites falling in along cosmic filaments, from ancient group infall events, or from some other mechanism remains an active area of research. The total mass of the local group can be estimated through several independent methods, each probing different aspects of the gravitational dynamics. The timing argument, first applied by astronomers Franz Kahn and Ludovic Voltier in 1959, uses the fact that the Milky Way and Andromeda are approaching each other despite the universe's expansion. For two objects that started moving apart with the Hubble flow after the Big Bang to have reversed their motion and now be falling together, their combined mass must exceed a certain threshold. Modern applications of this argument, refined with precise distance and velocity measurements, yield a local group mass between 4 and 5 trillion solar masses. Velocity dispersion measurements offer another approach. By measuring the speeds at which dwarf galaxies move relative to the group's center of mass, astronomers can apply the virial theorem to estimate the total gravitating mass required to keep these objects bound. The velocities observed, typically 60 to 100 kilometers per second relative to the group barycenter, imply a total mass consistent with the timing argument estimates. Both methods confirm that the visible stars and gas account for only a small fraction of the local group's gravitating material, with dark matter comprising roughly 90% of the total mass. The barycenter of the local group, the center of mass around which all members orbit, lies in the space between the Milky Way and Andromeda, closer to the more massive Andromeda. Current estimates place it approximately 1.5 million light-years from the Milky Way in the direction of Andromeda. Both giant spirals orbit this invisible point, though their orbital period around the common center of mass exceeds the current age of the universe. The system has not yet completed a single orbit since its formation. Beyond the two dominant spirals and their satellite swarms, the local group contains a handful of isolated dwarf galaxies that orbit neither giant directly. The Aquarius dwarf, the Sagittarius dwarf irregular galaxy, and the dwarf irregular Leo A all lie at distances exceeding 1 million light-years from both the Milky Way and Andromeda, moving through the group's outer regions on trajectories that may eventually bring them closer to one of the dominant members. These isolated dwarfs provide laboratories for studying galaxy evolution in the absence of strong tidal interactions. Their star formation histories shaped primarily by internal processes rather than external gravitational influences. The local group does not exist in isolation, but rather forms part of a larger structure. Neighboring galaxy groups lie scattered across the surrounding tens of millions of light-years, each representing a similar gravitationally bound collection of galaxies. The Sculptor Group, centered approximately 12 million light-years away, contains several spiral galaxies, including NGC 253, a starburst galaxy forming stars at roughly 10 times the Milky Way's rate. The Maffei group lies partially hidden behind the Milky Way's disk, its members obscured by dust and detectable primarily at infrared wavelengths. The Centaurus A group, dominated by the peculiar radio galaxy Centaurus A at a distance of roughly 12 million light-years, represents another nearby gravitational concentration. These neighboring groups, along with the local group itself, all fall within the gravitational influence of a much larger structure. They stream together through space, drawn toward a common attractor that operates on scales of hundreds of millions of light-years. The local group's motion through the cosmic microwave background radiation, measured at approximately 627 kilometers per second, reflects this larger gravitational pull. The modest collection of galaxies surrounding the Milky Way represents merely one node in a web of matter that extends far beyond what any single group contains. A web whose full architecture requires ascending to yet larger scales of cosmic structure. The gravitational web connecting these groups ensures that galaxies do not drift through the universe in isolation. Their paths inevitably cross, their dark matter halos overlap, and when they do, the physics of their encounters reshapes everything within them. Galaxy interactions represent one of the most transformative processes in cosmic evolution, converting orderly spiral structures into chaotic starbursts, triggering the birth of millions of new stars, and ultimately merging separate systems into entirely new configurations. The fundamental force driving these transformations is the tidal force, the same phenomenon that raises ocean tides on Earth, but operating across scales of tens of thousands of light-years. When two galaxies approach each other, the gravitational pull on the near side of each galaxy exceeds the pull on the far side. This differential creates a stretching effect, elongating each galaxy along the axis connecting them. For a galaxy like the Milky Way, approximately 100,000 light-years in diameter, an approaching companion of similar mass creates a gravitational gradient that can extract stars from their normal orbits and fling them into vast tidal streams, extending hundreds of thousands of light-years into intergalactic space. The mathematics of tidal disruption follows from Newton's law of gravitation. The tidal force scales with the mass of the perturbing galaxy, and inversely with the cube of the distance between the two systems. This steep distance dependence means that tidal effects remain negligible when galaxies are separated by millions of light-years, but become dramatically important as they approach within a few 100,000 light-years of each other. At a separation of 100,000 light-years, a galaxy with the Milky Way's mass of approximately 1.5 trillion solar masses exerts tidal forces capable of stripping loosely bound stars from the outer regions of its companion. The antenna galaxies, catalogued as NGC 4038 and NGC 4039, provide one of the most spectacular examples of this process in action. Located approximately 45 million light-years away in the constellation Corvus, these two spiral galaxies began their interaction roughly 600 million years ago. Their first close passage extracted enormous tidal tails of stars and gas, each extending approximately 500,000 light-years from the main bodies of the galaxies. These tails contain billions of stars that once orbited peacefully within their parent disks, but now stream through intergalactic space, tracing the gravitational history of the encounter like contrails marking an aircraft's path. The collision has triggered an extraordinary burst of star formation within the antennae system. Where the gas disks of the two galaxies interpenetrate, compression waves propagate through the interstellar medium, raising gas densities above the threshold required for gravitational collapse. Observations with the Hubble Space Telescope reveal over 1,000 young star clusters forming in the overlap region, some containing hundreds of thousands of stars each. The star formation rate in the antennae exceeds that of the Milky Way by a factor of roughly 20, converting gas into stars at approximately 20 solar masses per year, compared to the Milky Way's more sedate rate of 1 to 3 solar masses per year. This enhancement of star formation during galaxy interactions follows predictably from the physics of gas dynamics. Unlike stars, which pass through each other during galaxy collisions like two swarms of bees interpenetrating without individual bees colliding, gas clouds cannot avoid interaction. The interstellar medium of one galaxy plows into the interstellar medium of the other at relative velocities of several hundred kilometers per second. These collisions generate shock waves that compress the gas, increasing its density and triggering the gravitational instabilities that lead to star formation. Simulations indicate that the star formation rate can increase by factors of 10 to 100 during the peak of a major merger, depending on the gas content of the progenitor galaxies. The mice galaxies, NGC 4676a and NGC 4676b, located approximately 290 million light-years away, display an earlier stage of this process. Their long tidal tails, which give the system its common name, extend roughly 300,000 light-years and contain streams of young blue stars formed from gas compressed during the interaction. The two galaxies are currently separated by about 100,000 light-years and will continue to orbit each other, losing energy through a process called dynamical friction. Each passage brings them closer together, and simulations predict they will fully merge within approximately 500 million years. Dynamical friction provides the mechanism by which galaxy mergers actually complete. When a galaxy moves through the dark matter halo of another, it gravitationally attracts the dark matter particles behind it, creating a wake of enhanced density. This wake exerts a gravitational pull backward on the moving galaxy, slowing it down and causing it to spiral inward. The process transfers orbital energy from the galaxy's relative motion into the random motions of dark matter particles and stars, gradually converting an initially unbound flyby into a bound orbit and eventually into a complete merger. The timescale for dynamical friction depends on the masses involved and the orbital parameters. For two galaxies of roughly equal mass, like the Milky Way and Andromeda, the merger timescale from first approach to final coalescence typically spans 1 to 3 billion years. Smaller galaxies merging with larger hosts experience proportionally longer friction timescales because their smaller masses generate weaker gravitational wakes. The Large Magellanic Cloud, with a mass roughly 1/10 that of the Milky Way, will require several billion years to spiral inward and merge with its host, despite already orbiting at a distance of only 160,000 light-years. The Andromeda Galaxy, Messier 31, approaches the Milky Way at approximately 110 kilometers per second. Currently separated by 2.5 million light-years, the two galaxies will experience their first close passage in roughly 4.5 billion years. Simulations of this future encounter, incorporating the measured velocities and masses of both systems, predict that the first passage will extract dramatic tidal tails from both galaxies, distorting their spiral structures beyond recognition. The cores will separate after this initial encounter, swing out to distances of several 100,000 light-years, then fall back together for a second passage. After 2 or 3 such oscillations spanning roughly 2 billion years, the two galaxies will finally coalesce into a single elliptical galaxy that astronomers have nicknamed Milky Way. The transformation from spiral to elliptical during major mergers results from the violent relaxation of stellar orbits. In an undisturbed spiral galaxy, stars follow relatively ordered paths, orbiting the galactic center in roughly circular trajectories within a flattened disk. The gravitational chaos of a major merger scrambles these orbits, converting the ordered rotation into random motion in all directions. The resulting stellar system has no preferred plane of rotation and settles into the spheroidal or ellipsoidal shape characteristic of elliptical galaxies. This process is essentially irreversible. Once the ordered disk structure is destroyed, no natural mechanism can recreate it. Minor mergers involving galaxies of very different masses produce different outcomes. When a small galaxy falls into a much larger host, it contributes its stars and dark matter to the larger system without fundamentally altering the host structure. The Milky Way has experienced numerous such minor mergers throughout its history. The Sagittarius Dwarf Elliptical Galaxy, currently being torn apart by tidal forces as it orbits through the Milky Way's halo, represents an ongoing example. Its stars are being stripped away and incorporated into tidal streams that wrap around the Milky Way, adding perhaps 100 million solar masses of stellar material to our galaxy's halo. Evidence for past minor mergers appears throughout the Milky Way's stellar halo. The Gaia spacecraft, which has measured precise positions and velocities for nearly 2 billion stars, has revealed numerous stellar streams and substructures that represent the debris of disrupted satellite galaxies. The Gaia Enceladus structure, discovered in 2018, represents the remnants of a galaxy that merged with the Milky Way approximately 10 billion years ago. This ancient merger contributed a significant fraction of the stars now found in the inner stellar halo, and may have thickened the Milky Way's disk, creating the thick disk component that contains older, more metal-poor stars than the thin disk. The frequency of galaxy interactions increases dramatically in denser environments. In the field, where galaxies are separated by millions of light-years, close encounters remain rare events occurring perhaps once per several billion years. In galaxy clusters, where hundreds or thousands of galaxies occupy a volume only a few million light-years across, interactions become commonplace. The high-velocity dispersions in clusters, typically 800 to 1,200 kilometers per second, mean that galaxies pass each other too quickly for mergers to complete. But repeated high-speed encounters still strip gas and stars from cluster members through a process called harassment. This environmental processing helps explain why elliptical and lenticular galaxies dominate cluster cores, while spirals prefer the lower-density outskirts. These dense environments where elliptical galaxies congregate and spirals fade represent the largest gravitationally bound structures in the universe. Galaxy clusters contain not dozens, but hundreds to thousands of member galaxies, all trapped within a shared gravitational potential well that spans 5 to 15 million light-years across. The total mass holding these systems together ranges from 100 trillion to 1 quadrillion solar masses, making clusters the heavyweight champions of cosmic architecture. Yet the galaxies themselves, those luminous points that first drew astronomers' attention, contribute only a few % of this staggering total. The rest hides in forms invisible to optical telescopes, but detectable through other means. The Coma cluster, located approximately 320 million light-years away in the constellation Coma Berenices, serves as the archetype for understanding these massive structures. Swiss astronomer Fritz Zwicky studied this system in 1933, measuring the velocities of individual galaxies as they orbited within the cluster's gravitational embrace. What he found troubled him deeply. The galaxies were moving far too fast, with velocity dispersions exceeding 1,000 kilometers per second, for the visible matter to hold them together. By his calculations, the cluster should have flown apart billions of years ago, its galaxies scattering into the cosmic void like seeds from a dandelion. Yet there it sat, a coherent structure containing over 1,000 galaxies, clearly bound by something his telescopes could not see. Zwicky coined the term dunkle materia, dark matter, to describe this missing mass. His estimates suggested the Coma cluster contained at least 400 times more matter than the visible galaxies could account for. Modern measurements have refined this ratio, finding that dark matter comprises roughly 80 to 85% of cluster mass, with ordinary baryonic matter making up the remainder. The galaxies themselves, those brilliant islands of stars that define the cluster visually, represent merely 1 to 2% of the total. They are foam on an invisible ocean, traces of a gravitational potential carved primarily by matter that neither emits nor absorbs light. This dark matter forms an enormous halo encompassing the entire cluster, its density highest at the center and declining smoothly towards the edges, following a profile mathematicians called the Navarro-Frank-White distribution. The dark matter particles, whatever they may be, orbit within this halo at speeds of roughly 1,000 to 1,500 kilometers per second, their random motions creating an outward pressure that balances gravitational collapse. This state of virial equilibrium allows the cluster to persist as a stable structure over billions of years, neither expanding nor contracting, but maintaining a dynamic balance between kinetic and potential energy. Between the galaxies, filling the vast spaces that appear empty in optical images, lurks another major component of cluster mass. The intracluster medium consists of extremely hot gas, primarily hydrogen and helium, with traces of heavier elements. heated to temperatures between 10 and 100 million Kelvin. At these temperatures, the gas becomes fully ionized plasma, its electrons stripped from atomic nuclei and moving independently at tremendous speeds. This thermal energy prevents the gas from collapsing further, supporting it against the cluster's gravitational pull in much the same way that pressure supports a star against its own weight. The intracluster medium reveals itself through X-ray emission, the hot plasma radiating photons as electrons scatter off ions in a process called thermal Bremsstrahlung. X-ray telescopes like Chandra and XMM Newton have mapped this emission in exquisite detail, revealing that the hot gas accounts for approximately 12 to 15% of cluster mass, far exceeding the contribution from galaxies themselves. In the Coma cluster, this gas extends across millions of light years, its total mass reaching several hundred trillion solar masses. The gas temperature, measured through the energy distribution of emitted X-rays, provides a direct probe of the gravitational potential depth. Hotter gas indicates a deeper potential well, which in turn implies greater total mass. The distribution of this hot gas traces the underlying dark matter distribution, pooling most densely where the gravitational potential reaches its minimum at the cluster center. There, at the bottom of this cosmic valley, sits the brightest cluster galaxy, typically a giant elliptical that has grown to enormous size through repeated mergers over billions of years. In the Coma cluster, two such giants dominate the core, NGC 4874 and NGC 4889, each containing several trillion solar masses and spanning hundreds of thousands of light years. NGC 4889 harbors one of the most massive black holes ever measured, with an estimated mass of 21 billion solar masses, a gravitational monster that grew fat on the gas and stars funneled toward the cluster center. These brightest cluster galaxies occupy a special position in the hierarchy of cosmic structure. They sit at the nodes where dark matter filaments converge, at the deepest points in the gravitational landscape, where matter naturally accumulates. Their growth reflects the growth of the cluster itself, as smaller galaxies fall inward, lose their gas to ram pressure stripping, and eventually merge with the central giant. The extended stellar halos surrounding these galaxies, visible as faint diffuse light stretching far beyond their main bodies, consist partly of stars torn from infalling victims during these cannibalistic encounters. Galaxy clusters do not form in isolation, but grow through the hierarchical merging of smaller structures. Groups containing a few dozen galaxies fall together, their dark matter halos overlapping and eventually merging into a single, larger halo. The process continues over billions of years, with clusters accreting material from surrounding filaments of the cosmic web. The Coma cluster itself shows evidence of ongoing assembly, with substructures visible in both the galaxy distribution and the X-ray emitting gas. A group of galaxies centered on NGC 4839 appears to be falling into the main cluster from the southwest, its gas trailing behind in a wake created by its passage through the intracluster medium. The velocity dispersion of cluster galaxies, that same measurement that first revealed dark matter to Zwicky, provides one method for estimating total cluster mass. Applying the virial theorem, which relates kinetic and potential energy in a bound system, astronomers can convert observed velocities into gravitational mass. For the Coma cluster, this yields a total mass of approximately 7 times 10 to the 15th solar masses, or about 7 quadrillion suns. Independent measurements using X-ray gas temperatures and gravitational lensing confirm this estimate, providing confidence that the dark matter paradigm correctly describes cluster dynamics. The space between cluster galaxies, despite being filled with hot gas, remains extraordinarily empty by terrestrial standards. The intracluster medium has a density of roughly 1 particle per 1,000 cubic centimeters, a vacuum far more perfect than anything achievable in Earth laboratories. Yet across the millions of light-years that clusters span, this tenuous gas accumulates to tremendous total mass. Its presence affects the galaxies embedded within it, stripping cold gas from spirals that venture too close to the cluster center and quenching their star formation. This environmental processing transforms blue, actively star-forming galaxies into red, quiescent systems, contributing to the morphology-density relation that astronomers observe across different cosmic environments. The Coma cluster stands as perhaps the most historically significant laboratory for understanding the dark matter problem. Located approximately 321 million light-years from Earth, in the direction of the constellation Coma Berenices, this massive aggregation of galaxies provided the first compelling evidence that the visible universe represents only a fraction of what actually exists. The cluster contains over 1,000 galaxies concentrated within a region roughly 20 million light-years across, their combined light creating a faint glow visible to amateur astronomers with modest telescopes. In 1933, Swiss astronomer Fritz Zwicky turned his attention to this distant congregation and performed a calculation that would reshape cosmology. He measured the velocities of individual galaxies within the cluster by analyzing the Doppler shifts in their spectra, finding that these galaxies moved at extraordinary speeds, some exceeding 2,000 kilometers per second relative to the cluster's center of mass. Such velocities seemed impossibly high. When Zwicky applied the virial theorem, a fundamental relationship from classical mechanics that connects the kinetic energy of a system to its gravitational potential energy, he discovered a profound discrepancy. The virial theorem states that for a gravitationally bound system in equilibrium, the total kinetic energy equals negative 1/2 the gravitational potential energy. This relationship allows astronomers to estimate the total mass of a cluster by measuring how fast its member galaxies move. Faster motions require deeper gravitational wells to prevent the system from flying apart, which in turn requires more mass. When Zwicky performed this calculation for the Coma cluster, he found that the galaxies were moving so rapidly that the cluster should have dispersed long ago, its members scattering into intergalactic space like droplets from a spinning wheel. The mass required to gravitationally bind the Coma cluster, to keep those 1,000+ galaxies orbiting within their common potential well, exceeded the visible mass by a factor of several hundred. Zwicky estimated that the cluster needed approximately 400 times more mass than the luminous matter could account for. He called this missing component Dunkelmaterie, dark matter, a term that would eventually become one of the most important concepts in modern astrophysics. The visible galaxies, with all their hundreds of billions of stars, represented merely the luminous traces of a far more massive, invisible structure. Modern measurements have refined Zwicky's original estimates while confirming his fundamental insight. The Coma cluster has a total mass of approximately 7 times 10 to the 15th solar masses, a number so large it defies intuitive comprehension. If the Sun represents a single grain of sand, the Coma cluster contains enough mass to fill several Olympic swimming pools with such grains. Yet the stars within the cluster's galaxies account for only about 2% of this total. The hot intracluster gas, detected through its X-ray emissions, contributes another 13% or so. The remaining 85% consists of dark matter, invisible to all electromagnetic observations, but absolutely essential for the cluster's gravitational coherence. The 2 dominant galaxies at the Coma cluster's center, designated NGC 4874 and NGC 4889, exemplify the massive ellipticals that form through repeated mergers in such dense environments. NGC 4889 harbors one of the most massive black holes ever measured, with a mass estimated between 6 and 37 billion solar masses, a range that reflects the difficulty of precise measurements at such distances. This supermassive black hole exceeds the mass of Sagittarius A star at the Milky Way's center by more than 1,000 times, a testament to the violent merger history that built this giant elliptical galaxy. The velocity dispersion of galaxies within the Coma cluster, the statistical spread of their individual motions around the mean cluster velocity, provides the key observable for virial mass calculations. This dispersion measures approximately 1,000 kilometers per second, meaning that typical galaxies within the cluster move at speeds that would carry them from Earth to the Moon in about 6 minutes. Such velocities would tear the cluster apart within a few 100 million years if only the visible matter provided gravitational binding. The cluster's age, estimated at several billion years based on the stellar populations of its member galaxies, proves that additional mass must be present. X-ray observations from space telescopes like Chandra and XMM Newton reveal the hot gas that pervades the space between Coma's galaxies. This intracluster medium reaches temperatures of approximately 100 million Kelvin, so hot that it emits primarily in X-ray wavelengths invisible from Earth's surface. The gas distribution traces the gravitational potential of the cluster, settling into the valleys carved by dark matter just as water pools in topographic depressions. By measuring how the gas density and temperature vary with distance from the cluster center, astronomers can reconstruct the total mass profile, finding results consistent with the virial theorem calculations. The Coma cluster does not exist in isolation, but forms part of a larger structure called the Coma Supercluster, which extends across hundreds of millions of light years. The cluster itself shows evidence of ongoing assembly, with substructures and asymmetries in its galaxy distribution suggesting recent or ongoing mergers with smaller groups. A prominent feature called the NGC4839 group appears to be falling into the main cluster from the southwest, its galaxies and gas being incorporated into the larger structure. This hierarchical growth smaller systems merging to form larger ones, represents the fundamental process by which cosmic structure develops over billions of years. Gravitational lensing provides an independent method for measuring the coma cluster's mass, one that does not rely on assumptions about the system being in virial equilibrium. When light from more distant galaxies passes through the cluster, the intervening mass bends and distorts these background images. The degree of distortion depends on the total mass along the line of sight, regardless of whether that mass is luminous or dark. Weak lensing analyses of the coma cluster yield mass estimates consistent with those derived from galaxy velocities and X-ray gas distributions, providing powerful confirmation that dark matter dominates the cluster's mass budget. The dark matter within the coma cluster does not distribute itself uniformly, but concentrates towards the center, while extending in a diffuse halo far beyond the visible galaxy distribution. Simulations suggest that this dark matter halo follows a density profile that rises steeply toward the center, though the exact shape remains a subject of ongoing research. Individual galaxies within the cluster retain their own dark matter subhalos, smaller concentrations embedded within the larger cluster halo, like raisins in a pudding. These subhalos experience tidal stripping as galaxies orbit through the cluster, gradually losing their outer dark matter to the common cluster potential. The intracluster medium in coma shows complex structure when examined in detail. Shock fronts and cold fronts, sharp discontinuities in gas temperature and density reveal the dynamic history of the cluster. These features form when subclusters merge, their gas components colliding and heating while their dark matter halos pass through each other relatively unimpeded. The different behavior of gas and dark matter during mergers provides crucial evidence about dark matter's properties, demonstrating that it interacts gravitationally but not through electromagnetic forces or strong nuclear interactions. Radio observations reveal another component of the coma cluster's ecosystem. A diffuse radio halo spans the central region, produced by relativistic electrons spiraling through weak magnetic fields that thread the intracluster medium. These electrons likely gained their extreme energies during merger events, when shock waves accelerated particles to velocities approaching the speed of light. The radio halo traces the turbulent history of the cluster, a fossil record of past collisions written in radio waves. The coma cluster's distance of 321 million light-years places it far enough that cosmological effects begin to matter. Light from the cluster left its galaxies when multicellular life on Earth was just beginning to diversify in the oceans of the Ediacaran period. The cluster we observe today represents a snapshot of conditions hundreds of millions of years in the past, a time capsule from an earlier cosmic epoch. Yet even at this distance, the coma cluster remains close enough for detailed study, its galaxies resolvable as individual objects rather than blurred smears of light. The galaxies themselves, as luminous and massive as they appear, represent only a fraction of the ordinary matter within a cluster like coma. Between these stellar islands stretches a vast ocean of superheated gas, known as the intracluster medium, a diffuse plasma that outweighs all the cluster's stars combined by a factor of roughly 5 to 1. If the galaxies are the visible peaks of mountains, the intracluster medium is the atmosphere that fills every valley and canyon between them, invisible to optical telescopes but blazing with energy in the X-ray portion of the electromagnetic spectrum. This gas reaches temperatures that seem almost impossible to comprehend. Within the coma cluster, the intracluster medium burns at approximately 100 million Kelvin, nearly 10 times hotter than the core of the Sun, where nuclear fusion transforms hydrogen into helium. At such extreme temperatures, atoms cannot hold on to their electrons. Hydrogen exists not as neutral atoms, but as a plasma of free protons and electrons, while heavier elements like iron, oxygen, and silicon have been stripped of most or all of their electron shells. These ions and electrons race through the cluster volume at velocities of roughly 1,000 kilometers per second. Their thermal motion so violent that the gas would expand and dissipate into intergalactic space within a few 100 million years, if not for the gravitational grip of the cluster's dark matter halo. The origin of this extreme temperature lies in the physics of gravitational collapse. As matter fell into the cluster's gravitational potential well over billions of years, it converted gravitational potential energy into kinetic energy. Much like a ball rolling down a hill gains speed. For gas, this kinetic energy manifests as thermal motion, the random velocities of individual particles that we measure as temperature. The deeper the gravitational well, the faster the infalling material must move to reach equilibrium, and the hotter the resulting gas becomes. The coma cluster's potential well, carved primarily by its dark matter halo of roughly 700 trillion solar masses, is deep enough to heat gas to these extraordinary temperatures through gravitational compression alone, without any need for nuclear reactions or external energy sources. The density of this plasma remains remarkably low by terrestrial standards. Near the cluster center, the intracluster medium contains perhaps 1,000th of a particle per cubic centimeter, a vacuum far more perfect than anything achievable in Earth-based laboratories. The best vacuum chambers on Earth contain roughly 100,000 particles per cubic centimeter, making the cluster core approximately 100 million times emptier. Yet this tenuous gas extends across such enormous volumes, spanning millions of light years in every direction, that its total mass reaches staggering values. The coma cluster's intracluster medium contains approximately 100 trillion solar masses of hot plasma, enough material to build hundreds of billions of stars if it could somehow cool and condense. The challenge of cooling presents one of the most intriguing puzzles in cluster physics. At 100 million Kelvin, the plasma radiates energy primarily through a process called thermal Bremsstrahlung, or breaking radiation. When free electrons pass close to ions, they experience electromagnetic deflection that causes them to emit X-ray photons. This radiation carries energy away from the gas, and simple calculations suggest that the dense central regions of clusters should cool significantly over cosmic timescales. In the coma cluster's core, the cooling time, the time required for the gas to radiate away its thermal energy, drops to roughly 10 billion years, comparable to the age of the universe itself. Yet observations reveal that the expected cooling rarely occurs as predicted. The central gas in most clusters remains hot, suggesting that some heating mechanism must balance the radiative losses. Astronomers now believe that supermassive black holes at the centers of the brightest cluster galaxies provide this feedback. These black holes, with masses of billions of solar masses, periodically accrete surrounding material and launch powerful jets of relativistic particles that inflate enormous bubbles in the intracluster medium. These bubbles, visible as cavities in X-ray images, transfer energy to the surrounding gas through a combination of shock heating and turbulent mixing. The Coma Cluster's central galaxy, NGC 4889, harbors one of the most massive black holes ever measured, with an estimated mass of 21 billion solar masses, a gravitational engine capable of influencing gas across hundreds of thousands of light-years. The chemical composition of the intracluster medium tells a story of stellar evolution across cosmic time. Roughly 75% of the plasma consists of hydrogen, with another 24% helium, proportions that reflect the primordial abundances created in the Big Bang. But the remaining 1% contains heavier elements, iron, oxygen, silicon, sulfur, and others, that could only have been forged in the nuclear furnaces of stars and distributed by supernova explosions. The iron abundance in the Coma Cluster's intracluster medium reaches approximately 1/3 of the solar value, meaning that for every million hydrogen atoms, there are roughly 10 iron atoms. This iron mass, totaling perhaps 10 billion solar masses across the entire cluster, represents the accumulated output of trillions of supernova explosions over the past 10 billion years. The distribution of these metals provides clues about how they escaped from galaxies into the surrounding medium. Near the cluster center, iron abundances peak, suggesting that the massive elliptical galaxies concentrated there have been particularly efficient at enriching their surroundings. The enrichment mechanisms include supernova-driven galactic winds, ram pressure stripping that tears gas from infalling spiral galaxies, and tidal interactions that liberate stellar material during galaxy mergers. Each process leaves distinctive signatures in the metal distribution patterns, allowing astronomers to reconstruct the chemical history of the cluster environment. X-ray telescopes have revolutionized our understanding of the intracluster medium. The Chandra X-ray Observatory, with its sub-arcsecond angular resolution, can map temperature and density variations across cluster volumes with unprecedented detail. These maps reveal that the intracluster medium is far from uniform. Shock fronts mark the boundaries where infalling groups have collided with the main cluster, compressing and heating the gas to even higher temperatures. Cold fronts, sharp discontinuities where cooler, denser gas meets hotter, more diffuse material, trace the sloshing motions induced by past merger events. The Coma Cluster displays both features, evidence of its dynamic history as a growing structure that continues to accrete smaller systems from the surrounding cosmic web. The X-ray observations that reveal the hot intracluster medium provide one method for measuring the mass of galaxy clusters, but nature offers another tool, one that relies on the geometry of space-time itself. When light from distant galaxies passes near a massive foreground cluster, it does not travel in a straight line. The mass of the cluster warps the fabric of space-time, bending the paths of photons that traverse this curved geometry. This phenomenon, predicted by Einstein's general theory of relativity in 1915 and first confirmed during a solar eclipse in 1919, becomes a powerful astronomical instrument when applied to the enormous masses concentrated in galaxy clusters. The principle operates much like a glass lens, though the physics differs fundamentally. A glass lens bends light through refraction, the change in speed as photons enter a denser medium. A gravitational lens bends light through the curvature of space-time itself, requiring no physical material in the light's path. The deflection angle depends on the mass enclosed within the light's closest approach to the lens and the geometry of the source, lens, and observer. For a point mass, Einstein calculated that light grazing the surface of the Sun would deflect by approximately 1.75 arcseconds, a tiny angle, but one large enough to measure during an eclipse when stars near the solar limb become visible. Galaxy clusters produce deflections thousands of times stronger. A cluster with a mass of 10 to the 15th solar masses, 10 quadrillion times the mass of our Sun, can bend light from background galaxies by tens of arcseconds. This deflection does not merely shift the apparent positions of distant sources. It distorts their shapes, stretches their images tangentially around the cluster center, and in extreme cases produces multiple images of the same background galaxy appearing at different positions in the sky. These dramatic effects transform galaxy clusters into cosmic telescopes, magnifying and distorting the light from objects far more distant than the cluster itself. Astronomers distinguish between strong and weak gravitational lensing based on the magnitude of the distortion. Strong lensing occurs in the dense central regions of massive clusters, where the surface mass density exceeds a critical threshold. This critical density depends on the angular diameter distances between observer, lens, and source, typically falling around 0.3 to 0.5 grams per square centimeter for clusters at cosmological distances. When the projected mass density surpasses this value, multiple images form. Background galaxies can appear as luminous arcs, their circular shapes stretched into thin crescents that curve around the cluster core. In the most symmetric configurations, a background source aligned precisely behind the cluster center produces an Einstein ring, a complete circle of light surrounding the lens. The cluster Abel 370, located approximately 4 billion light-years from Earth, displays one of the most spectacular examples of strong gravitational lensing. A giant luminous arc stretches across nearly 100,000 light-years in projected length, the distorted image of a spiral galaxy lying roughly twice as far away as the cluster itself. This arc represents a magnification factor of approximately 20, meaning the background galaxy appears 20 times brighter than it would without the intervening cluster. The Hubble Space Telescope has captured dozens of such arcs in massive clusters, each one a stretched and amplified portrait of a galaxy that would otherwise remain too faint to study in detail. The positions, shapes, and brightnesses of these strongly lensed images encode precise information about the mass distribution in the foreground cluster. By measuring the locations of multiple images and arcs, astronomers can reconstruct the projected mass density across the cluster core. This technique reveals that the mass does not follow the distribution of visible galaxies. Instead, it traces a smoother, more extended profile consistent with a dark matter halo that dominates the gravitational potential. The mass-to-light ratio in cluster cores typically exceeds 200 solar masses per solar luminosity, meaning that for every unit of light the cluster produces, more than 200 times that mass must be present in some non-luminous form. Beyond the central strong lensing region, the cluster's gravitational influence extends to much larger radii, producing weak lensing effects that require statistical analysis to detect. Individual background galaxies experience small distortions, typically stretching their shapes by only a few %. A circular galaxy might appear slightly elliptical, with its major axis oriented tangentially to the cluster center. This distortion is far smaller than the intrinsic ellipticity of most galaxies, which already possess elongated shapes due to their rotation, inclination, and structural properties. No single weakly lensed galaxy reveals the cluster's mass. Instead, astronomers must average the shapes of thousands of background sources, looking for the coherent tangential alignment that the cluster's gravity imprints on the population. This statistical approach requires careful calibration. Astronomers must estimate the intrinsic shape distribution of unlensed galaxies, account for the point spread function of the telescope that blurs images, and separate foreground cluster members from the background population being lensed. Color information helps with this separation, as background galaxies at higher redshifts appear redder due to the expansion of the universe stretching their light to longer wavelengths. Photometric redshift techniques, which estimate distances from the colors of galaxies measured through multiple filters, allow astronomers to construct catalogs of probable background sources suitable for weak lensing analysis. The weak lensing signal around a massive cluster like Coma extends to radii of 10 megaparsecs or more, far beyond the region where X-ray emission from the intracluster medium can be detected. This extended reach makes weak lensing the most direct probe of the total mass distribution, including the outer regions of the dark matter halo, where the density falls below the threshold for producing observable X-ray emission. Measurements of the Coma cluster using weak lensing data from wide-field surveys yield total masses of approximately 7 times 10 to the 14th solar masses within a radius of 2.7 megaparsecs, consistent with the virial mass estimates derived from galaxy velocities, but extending the measurement to larger scales. The agreement between independent mass estimation techniques, velocity dispersions, X-ray temperatures, and gravitational lensing provides powerful confirmation that dark matter dominates the mass budget of galaxy clusters. Each method relies on different physical principles and different assumptions. Velocity dispersions assume the cluster has reached virial equilibrium. X-ray measurements assume the gas is in hydrostatic balance with the gravitational potential. Gravitational lensing makes no assumptions about the dynamical state of the cluster, responding only to the total projected mass along the line of sight. When all three methods converge on similar mass estimates, the case for dark matter becomes compelling. The Bullet Cluster, officially designated 1E0657-558, provides perhaps the most visually striking evidence for dark matter through gravitational lensing. This system consists of two galaxy clusters that collided approximately 150 million years ago, passing through each other at a relative velocity of roughly 4,500 kilometers per second. The collision separated the different mass components in a way that reveals their distinct behaviors. The hot intracluster gas, which interacts through electromagnetic forces, experienced ram pressure during the collision and now lags behind the cluster cores. X-ray observations show this gas concentrated between the two cluster centers, shock-heated to temperatures exceeding 100 million Kelvin. The galaxies within each cluster, behaving as collisionless particles that passed through each other without direct interaction, continued moving outward and now lead the gas distribution. Weak lensing maps of the bullet cluster reveal that the mass peaks do not coincide with the X-ray emission from the gas. Instead, the mass concentrations align with the galaxy distributions, offset from the gas by hundreds of kiloparsecs. This spatial separation demonstrates that most of the cluster mass consists of something that does not interact with ordinary matter except through gravity. The dark matter halos passed through each other like the galaxies, unimpeded by the collision that stripped and heated the gas. Quantitative analysis of the bullet cluster lensing data shows that the mass-to-light ratio in the regions around the galaxies exceeds 300, while the mass associated with the X-ray gas accounts for only about 15% of the total. The remaining 85% must reside in dark matter halos that trace the galaxy distribution rather than the gas. Alternative theories that attempt to explain cluster dynamics through modifications to gravity rather than dark matter struggle to reproduce this observation. Modified gravity would predict that the gravitational lensing signal should follow the distribution of ordinary matter, which in clusters is dominated by the hot gas. The bullet cluster shows the opposite, with mass concentrated where the dark matter halos should be, rather than where the baryons reside. Similar colliding cluster systems have been identified and analyzed, each providing additional evidence for the dark matter interpretation. Hubble 520, the musketball cluster, and Max J0025.4-1222 all show offsets between their gas and mass distributions consistent with dark matter halos that behave as collisionless components during mergers. These cosmic collisions serve as natural experiments, separating the visible and invisible matter in ways that laboratory experiments cannot achieve, revealing the gravitational scaffolding that shapes the largest structures in the universe. The gravitational scaffolding revealed by these colliding clusters extends far beyond the boundaries of any single cluster. Galaxy clusters themselves are not isolated islands, but rather nodes in a much larger network, connected by filaments of dark matter and ordinary matter that stretch across hundreds of millions of light years. When astronomers step back to view the universe at even larger scales, they find that clusters aggregate into still grander structures called superclusters, vast assemblages that represent the next level in the cosmic hierarchy of gravitationally influenced matter. The Virgo supercluster serves as the most thoroughly studied example of these enormous structures, primarily because it contains our own galaxy. The Milky Way resides not at the center of this supercluster, but in its outer regions, within the local group, which itself occupies a relatively sparse zone compared to the dense core. The Virgo supercluster spans approximately 110 million light-years in its longest dimension and contains at least 100 galaxy groups and clusters, with a total mass estimated at roughly 1 quadrillion solar masses, or about 10 to the 15th power times the mass of our Sun. At the heart of this supercluster lies the Virgo cluster, the gravitational anchor around which the surrounding groups orbit, or toward which they fall. The Virgo cluster contains approximately 1,300 to 2,000 galaxies, packed into a region only about 15 million light-years across, creating a concentration of mass so significant that its gravitational influence extends throughout the entire supercluster. The giant elliptical galaxy Messier 87 sits near the center of the Virgo cluster, harboring a supermassive black hole of 6.5 billion solar masses, the first black hole ever directly imaged by the Event Horizon Telescope. The gravitational pull of the Virgo cluster affects the motion of every galaxy in the supercluster, including our own. Astronomers measure this influence through a phenomenon called the Virgo-centric flow, the tendency of galaxies in the supercluster to move toward the Virgo cluster at velocities that exceed what would be expected from the general expansion of the universe alone. The local group approaches the Virgo cluster at approximately 300 kilometers per second, relative to the Hubble flow, drawn by the immense concentration of mass at the supercluster's core. This infell velocity provides another method for estimating the total mass of the Virgo cluster and the supercluster as a whole. By measuring how strongly the cluster's gravity perturbs the motions of surrounding galaxies, astronomers can calculate the mass required to produce such perturbations. These dynamical mass estimates consistently indicate that the Virgo supercluster contains far more mass than can be accounted for by visible galaxies and hot gas alone, reinforcing the dark matter paradigm established through studies of individual clusters. The structure of the Virgo supercluster is not spherical, but highly elongated and irregular, reflecting the complex history of its formation through hierarchical clustering. In this cosmological model, small structures form first and gradually merge to create larger ones. Dark matter halos around individual galaxies merged to form group-scale halos, which then fell together into cluster-scale halos, which are now in the process of assembling into supercluster-scale structures. The Virgo supercluster represents a snapshot of this ongoing process, a structure still in the act of formation, rather than a relaxed equilibrium system. Unlike galaxy clusters, superclusters are generally not gravitationally bound systems. The expansion of the universe acts against the gravitational attraction between their component clusters and groups, and in most cases, this expansion will eventually win. The Virgo supercluster will not collapse into a single massive structure, but will instead be stretched apart over cosmic time, with its outer regions receding from the core as the universe continues to expand. Only the densest central regions around the Virgo cluster itself will remain bound, while outlying groups like the local group may eventually drift away. This distinction between bound and unbound structures marks an important transition in the hierarchy of cosmic architecture. Stars are bound to galaxies, galaxies are bound to groups groups are bound to clusters, but superclusters represent the scale at which gravitational binding begins to fail. The critical density required for a region to collapse against cosmic expansion depends on its size, and superclusters are simply too large and too diffuse to overcome the relentless stretching of space. The Virgo supercluster is embedded within an even larger structure that astronomers have named Laniakea, a Hawaiian word meaning immense heaven. Laniakea encompasses the Virgo supercluster along with several neighboring superclusters, including the Hydra Centaurus supercluster and the Pavo Indus supercluster, all connected by filaments of galaxies and dark matter. The total extent of Laniakea reaches approximately 520 million light-years, containing roughly 100,000 galaxies with a combined mass of about 100 quadrillion solar masses. The identification of Laniakea came through careful mapping of galaxy velocities throughout the local universe. Astronomers traced the flow patterns of thousands of galaxies, identifying the basins of attraction toward which matter streams. Just as water flows downhill toward the lowest point in a landscape, galaxies flow through space toward the regions of highest gravitational potential. The boundary of Laniakea marks the watershed between galaxies flowing toward the Great Attractor, a massive concentration of matter at the supercluster's center, and those flowing toward other attractors in neighboring superclusters. The Great Attractor lies approximately 250 million light-years from Earth in the direction of the Centaurus constellation, hidden behind the dense star fields and dust clouds of the Milky Way's disk. For decades, astronomers detected its gravitational influence through the peculiar velocities of galaxies in our region of space, all of which showed a systematic drift toward this unseen mass concentration. X-ray observations and infrared surveys that can penetrate the galactic obscuration have revealed the Norma cluster at the heart of the Great Attractor region, a massive galaxy cluster that serves as the gravitational anchor for much of Laniakea. The hierarchical nature of cosmic structure becomes evident when examining these nested levels of organization. The Milky Way belongs to the local group, which belongs to the Virgo supercluster, which belongs to Laniakea, which connects to the even larger cosmic web that spans the observable universe. At each level, gravity has gathered matter into denser concentrations, with dark matter providing the invisible framework upon which ordinary matter accumulates. The formation of superclusters follows directly from the initial conditions of the universe. The tiny density fluctuations present in the cosmic microwave background, variations of only 1 part in 100,000, served as the seeds for all subsequent structure. Regions with slightly higher density attracted more matter through gravity, growing denser over time, while underdense regions became progressively emptier. Over 13.8 billion years, this process of gravitational amplification transformed the nearly uniform early universe into the complex web of filaments, clusters, and voids observed today. Computer simulations of cosmic structure formation reproduce the observed distribution of superclusters with remarkable fidelity. These simulations begin with initial conditions matching the cosmic microwave background and evolve the distribution of dark matter and ordinary matter forward in time, according to the laws of gravity and gas dynamics. The resulting structures, including the sizes, shapes, and clustering properties of superclusters, match observations of the real universe, providing strong support for the standard cosmological model. The density within superclusters varies enormously from their cores to their outskirts. At the center of the Virgo cluster, the density of galaxies exceeds the cosmic average by a factor of several hundred. In the filaments connecting clusters within the supercluster, the overdensity drops to perhaps 10 to 50 times the average. At the edges of the supercluster, where it borders the surrounding voids, the density approaches or falls below the cosmic mean, marking the transition to the vast, empty regions that occupy most of the universe's volume. Temperature variations accompany these density contrasts. The intracluster medium at the core of the Virgo cluster reaches temperatures of tens of millions of degrees, heated by gravitational compression and shock waves from infurling matter. The intergalactic medium in the filaments between clusters remains cooler, perhaps 1 million degrees or less, while the gas in voids may be cooler still, though detecting this tenuous material remains challenging with current instruments. The study of superclusters reveals the universe as a dynamic, evolving system rather than a static arrangement of objects. Galaxies stream along filaments toward cluster cores, clusters merge to form larger clusters, and superclusters stretch and deform under the competing influences of gravity and cosmic expansion. The Virgo supercluster that exists today differs from the structure that existed 1 billion years ago, and will differ from the structure that will exist 1 billion years hence. Cosmic architecture is not fixed but fluid, shaped by the same gravitational forces that govern the orbits of planets and the collisions of galaxies. The gravitational currents that shape the Virgo supercluster extend far beyond its traditional boundaries, reaching across hundreds of millions of light years to define a much larger coherent structure. In 2014, a team of astronomers led by R. Brent Tully used a new approach to mapping cosmic architecture, one based not on the positions of galaxies, but on their motions. By tracing the peculiar velocities of thousands of galaxies, measuring how they deviate from the smooth expansion of the universe, these researchers revealed that our cosmic neighborhood belongs to a supercluster far more extensive than previously recognized. They named this structure Laniakea, a Hawaiian word meaning immeasurable heaven. The key insight behind this discovery lies in understanding that galaxies do not simply ride the expansion of space like passive particles. Each galaxy also experiences gravitational attraction from the matter around it, and this attraction produces peculiar velocities, motions that add to or subtract from the pure Hubble flow. A galaxy being pulled toward a massive concentration will appear to recede from us slightly slower than the expansion alone would predict, while a galaxy on the far side of that concentration will appear to recede slightly faster. By measuring these velocity deviations for approximately 8,000 galaxies within 300 million light-years, Tully's team could reconstruct the underlying gravitational field and identify the basins of attraction that define supercluster boundaries. The technique relies on a fundamental relationship between velocity and gravitational potential. In regions where matter is concentrated, galaxies flow inward like water draining toward the lowest point in a landscape. The boundaries between superclusters correspond to gravitational watersheds, surfaces where the flow direction changes. A galaxy on one side of this boundary will ultimately fall toward one attractor, while a galaxy on the other side will fall toward a different attractor. These boundaries are not walls or barriers, but rather the crests of gravitational hills, the ridgelines that separate one drainage basin from another. Laniakea, as revealed by this velocity flow analysis, spans approximately 520 million light-years in its greatest extent and contains roughly 100,000 galaxies with a total mass of about 100 million billion solar masses. This makes it one of the larger superclusters identified in the nearby universe, though not the largest. The structure encompasses not only the Virgo supercluster, but also several other previously recognized superclusters, including the Hydra Centaurus supercluster and the Pavo Indus supercluster. What appeared as separate structures in earlier surveys turned out to be connected regions within a single gravitational basin. At the heart of Laniakea lies a region of concentrated mass, known as the Great Attractor. Located approximately 250 million light-years from Earth, in the direction of the constellation Centaurus. This gravitational focal point was first identified in the 1970s and 1980s through observations of galaxy peculiar velocities, which showed that the Milky Way and its neighbors are moving toward this region at approximately 600 kilometers per second relative to the cosmic microwave background. For decades, the nature of the Great Attractor remained mysterious, partly because it lies behind the plane of our own galaxy, where dust and stars obscure the view of distant objects. The velocity flow mapping revealed that the Great Attractor is not a single massive object, but rather a broad concentration of galaxy clusters and groups, with the Norma cluster serving as one of its most massive components. The Norma cluster, also known as Abell 3627, contains several hundred galaxies and lies approximately 220 million light-years away. Its mass, estimated at several hundred trillion solar masses, contributes significantly to the gravitational pull that defines the center of Laniakea. But the Great Attractor region as a whole represents the convergence point of multiple filaments and walls, a node in the cosmic web where matter has accumulated over billions of years. The motion of our local group toward the Great Attractor represents only part of a larger flow pattern. The entire Laniakea Supercluster, including the Great Attractor itself, appears to be moving toward an even more massive concentration known as the Shapley Supercluster, located approximately 650 million light-years away. The Shapley Supercluster contains more than 24 rich galaxy clusters, including Abell 3558 and Abell 3556, packed into a region spanning roughly 400 million light-years. Its total mass exceeds 10,000 trillion solar masses, making it one of the most massive concentrations of matter in the nearby universe. This nested hierarchy of motions, with smaller structures falling toward larger attractors, reflects the ongoing process of gravitational assembly that has shaped cosmic architecture since the earliest epochs. The boundaries of Laniakea are not sharp edges, but gradual transitions where the gravitational influence of one supercluster gives way to another. On one side, Laniakea borders the Perseus-Pisces supercluster, a chain of galaxy clusters stretching across 300 million light-years. On another side lies the Coma supercluster, home to the Coma cluster that provided early evidence for dark matter. These neighboring structures have their own internal velocity flows, their own basins of attraction, their own gravitational watersheds. The boundaries between them mark the surfaces where a galaxy's fate changes, where the direction of its ultimate infall switches from one attractor to another. The discovery of Laniakea illustrates how our understanding of cosmic structure depends on the tools and methods we use to observe it. Traditional surveys based on galaxy positions revealed clusters and apparent superclusters, but they could not distinguish between structures that happened to lie near each other in projection and structures that were genuinely connected by gravitational flows. The velocity-based approach cuts through this ambiguity by tracing the actual dynamics of the system, revealing which galaxies are bound together in a common gravitational embrace and which merely appear close by chance. The peculiar velocity measurements that enabled this mapping come from a technique called the Tully-Fisher relation for spiral galaxies and the fundamental plane for elliptical galaxies. These methods allow astronomers to estimate the intrinsic luminosity of a galaxy from its observable properties, such as rotation speed or velocity dispersion. Comparing this intrinsic luminosity to the observed brightness yields a distance estimate independent of redshift. The difference between this distance and the distance inferred from redshift alone reveals the peculiar velocity, the galaxy's motion relative to the Hubble flow. Accumulating these measurements for thousands of galaxies creates a three-dimensional velocity field that traces the underlying gravitational potential. Within Laniakea, the velocity flows reveal a complex internal structure. Galaxies in the outer regions stream inward at speeds of several hundred kilometers per second, while those closer to the great attractor move more slowly as they approach the bottom of the gravitational well. The flow lines converge toward the central concentration, but do not all reach it directly. Many galaxies follow curved paths, deflected by intermediate concentrations of mass, spiraling inward along the filaments that connect clusters and groups. The overall pattern resembles water flowing down a mountainside, finding channels and valleys, pooling in basins, eventually draining toward the lowest point. The timescales for these motions stretch across billions of years. A galaxy currently located at the edge of Laniakea, moving inward at 300 kilometers per second, would require roughly 500 million years to travel 500 million light-years, assuming constant velocity. But the velocity is not constant. As the galaxy falls deeper into the gravitational potential, it accelerates, gaining speed as it converts gravitational potential energy into kinetic energy. Meanwhile, the cosmic expansion continues to stretch the distances between structures, partially counteracting the infall. The competition between gravitational attraction and cosmic expansion determines whether Laniakea will eventually collapse into a single bound structure or gradually disperse as the universe continues to expand. Current evidence suggests that Laniakea as a whole is not gravitationally bound. The expansion of the universe is carrying its outer regions away faster than gravity can pull them back. Over cosmic time, the supercluster will not collapse into a single massive cluster, but will instead fragment, with only the densest central regions remaining bound while the periphery drifts away. The Virgo cluster and the Great Attractor region may eventually merge, but the more distant parts of Laniakea will become increasingly isolated, carried apart by the accelerating expansion driven by dark energy. This fate distinguishes superclusters from the smaller structures within them. Galaxy clusters like Virgo and Coma are gravitationally bound and will persist as coherent objects for the foreseeable cosmic future. But superclusters exist at the threshold of gravitational binding, large enough to influence the motions of their constituent galaxies, but not dense enough to overcome the expansion of space. They represent the largest scale at which gravity has produced coherent structures, the upper limit of hierarchical clustering in a universe dominated by dark energy. Beyond the boundaries of Laniakea, beyond the gravitational watersheds that define individual superclusters, the universe reveals its deepest architectural pattern. The distribution of matter across billions of light-years is neither random nor uniform, but organized into a vast, interconnected network that astronomers call the cosmic web. This structure, spanning the entire observable universe, represents the ultimate expression of gravitational physics operating over 13.8 billion years of cosmic history. The cosmic web consists of three primary components: filaments, walls, and nodes. The nodes are the densest concentrations, the galaxy clusters and superclusters where matter has accumulated most intensely. The filaments are elongated bridges of galaxies and dark matter stretching between these nodes, some extending for hundreds of millions of light-years. The walls are flattened sheets of galaxies, thinner than filaments but broader in extent, forming the boundaries between vast, empty regions. Together, these structures create a foam-like geometry, with dense matter concentrated along the surfaces and edges of bubble-like voids. The largest filaments in the observable universe contain thousands of galaxies strung along their lengths like pearls on a cosmic thread. The Perseus-Pisces supercluster, for instance, forms part of a filament extending over 300 million light-years, connecting multiple galaxy clusters in a gravitationally coherent chain. The galaxies within such filaments are not randomly oriented, but tend to align their spin axes with the filament direction, evidence that the large-scale gravitational field has influenced their formation and evolution. The physics underlying filament formation traces back to the earliest moments of cosmic structure development. In the primordial universe, dark matter was distributed almost uniformly, with density variations of only about 1 part in 100,000. These tiny fluctuations, imprinted during the inflationary epoch, provided the seeds from which all structure would grow. As the universe expanded and cooled, regions with slightly higher density began to attract surrounding matter through gravity, while regions with slightly lower density lost matter to their denser neighbors. The geometry of gravitational collapse in 3 dimensions naturally produces filamentary structures. Consider a region of space with a slight overdensity. If this region is perfectly spherical, it will collapse symmetrically toward its center, eventually forming a compact object. But primordial density fluctuations were rarely perfectly spherical. Most had slightly elongated or flattened shapes, and gravitational collapse amplifies these asymmetries, An elongated overdensity collapses fastest along its shortest axis, becoming progressively more elongated as it evolves. This process, called anisotropic collapse, naturally produces the filaments and walls observed in the cosmic web. Computer simulations of cosmic structure formation, such as the Millennium simulation and its successors, have reproduced this web-like architecture with remarkable fidelity. These simulations begin with the measured properties of the early universe, including the spectrum of primordial density fluctuations observed in the cosmic microwave background, and evolve them forward using the laws of gravity and hydrodynamics. The resulting structures match the observed distribution of galaxies in surveys like the Sloan Digital Sky Survey, which has mapped the positions of over 2 million galaxies across a significant fraction of the observable universe. The Sloan Digital Sky Survey revealed the cosmic web in unprecedented detail when it began releasing data in the early 2000s. By measuring the redshifts of galaxies, astronomers could determine their distances and construct three-dimensional maps of the matter distribution. These maps showed galaxies clustered along filaments and walls, with vast empty voids between them. The typical spacing between filaments is roughly 400 million light-years, though this varies considerably across different regions of the universe. Dark matter provides the gravitational scaffolding upon which the cosmic web is built. Ordinary matter, the atoms that form stars and planets and gas clouds, constitutes only about 16% of the total matter in the universe. The remaining 84% is dark matter, which interacts gravitationally but not electromagnetically. Dark matter began clustering earlier than ordinary matter because it was not coupled to the radiation field that filled the early universe. By the time ordinary matter decoupled from radiation, about 380,000 years after the Big Bang, dark matter had already begun forming the filamentary network that would later guide the flow of baryonic matter. The relationship between dark matter and ordinary matter in the cosmic web resembles water flowing through channels carved into a landscape. The dark matter filaments act as gravitational valleys, drawing ordinary matter toward them. Gas flows along these filaments toward the densest nodes, where it accumulates and eventually forms galaxies and galaxy clusters. This process explains why galaxies are not distributed randomly through space, but are concentrated along the filaments and at the intersections where multiple filaments meet. The walls of the cosmic web are perhaps its most visually striking features when viewed in large-scale surveys. These structures can extend for billions of light-years while remaining relatively thin, sometimes only 20 to 30 million light-years across. The CFA-2 Great Wall, discovered in 1989 by Margaret Geller and John Huchra, was one of the first such structures identified. It spans approximately 500 million light-years and contains thousands of galaxies arranged in a flattened sheet. This discovery fundamentally changed astronomers' understanding of the universe's large-scale structure, revealing that matter was organized into far larger coherent patterns than previously imagined. The nodes of the cosmic web, where filaments intersect, host the most massive gravitationally bound structures in the universe. Galaxy clusters like Coma and Virgo occupy these nodal positions, fed by streams of galaxies and gas flowing along the connecting filaments. The mass of a cluster correlates with the number and thickness of the filaments feeding it, with the most massive clusters typically sitting at the intersection of 4 or more major filaments. The Shapley Supercluster, one of the most massive concentrations of matter in the nearby universe, lies at such a nexus, drawing material from multiple directions. The temperature of gas within the cosmic web varies dramatically depending on location. In the densest regions, within galaxy clusters, the gas reaches temperatures of 10 to 100 million Kelvin, heated by gravitational compression and shock waves from infalling material. But the filaments themselves contain gas at intermediate temperatures, typically between 100,000 and 10 million Kelvin. This warm-hot intergalactic medium, as astronomers call it, contains a significant fraction of the ordinary matter in the universe, perhaps 40 to 50% of all baryons. Detecting this diffuse, moderately hot gas remains one of the observational challenges in modern cosmology. Recent observations have begun to directly image the cosmic web's structure. In 2019, astronomers using the Keck telescope detected hydrogen gas glowing in a filament connecting galaxies in the SSA 22 protocluster, located about 12 billion light-years away. This observation provided direct evidence that filaments contain substantial amounts of gas, not just galaxies and dark matter. The gas was illuminated by the intense ultraviolet radiation from young galaxies and quasars within the protocluster, causing it to fluoresce like a cosmic neon sign. The geometry of the cosmic web is not static, but continues to evolve. Filaments grow thicker as more matter flows along them toward the nodes. Smaller filaments merge into larger ones, while the voids between them expand as matter drains away. This evolution proceeds slowly by human standards, with significant changes occurring over timescales of billions of years. But computer simulations can compress this evolution into visualizations that reveal the dynamic nature of the web, showing matter streaming along filaments like traffic on cosmic highways, accumulating at the intersections where clusters grow ever more massive. The cosmic web represents the largest scale at which the universe displays significant structure. On scales larger than about 1 billion light-years, the distribution of matter becomes increasingly uniform, approaching the homogeneity assumed in cosmological models. This transition from structured to homogeneous marks the boundary between the realm of gravitational clustering and the realm of cosmic expansion, where the geometry of space-time itself becomes the dominant factor, shaping the universe's properties. The visible galaxies that trace the cosmic web represent only the luminous tips of far more massive structures. For every kilogram of ordinary matter that emits light, absorbs radiation, or participates in nuclear fusion, approximately 5 kilograms of dark matter exert their gravitational influence invisibly. This ratio, measured through multiple independent methods, reveals that the cosmic web we observe in galaxy surveys is merely a glowing outline of a much more substantial scaffolding, one that shaped the universe's structure long before the first stars ignited. Dark matter's existence was first suspected in the 1930s when Fritz Zwicky measured the velocities of galaxies in the Coma cluster and found them moving far too quickly to be held together by the visible matter alone. The galaxies should have dispersed into intergalactic space billions of years ago, yet they remained gravitationally bound. Something unseen was providing the additional mass necessary to keep the cluster intact. Zwicky estimated that this invisible component outweighed the luminous matter by a factor of several hundred, a calculation that proved remarkably prescient despite the crude instruments of his era. The evidence has only strengthened in the decades since. Rotation curves of spiral galaxies show stars in their outer regions orbiting at velocities that remain constant rather than declining with distance from the galactic center, as Newtonian mechanics would predict for a system where most mass is concentrated in the visible disk and bulge. This flat rotation curve, observed in galaxy after galaxy, implies that each spiral is embedded within an extended halo of invisible matter that extends far beyond the luminous boundaries. The Milky Way's dark matter halo, for instance, likely extends to a radius of approximately 300,000 light-years, roughly 3 times the diameter of the visible disk, and contains a total mass of about 1 trillion solar masses. Gravitational lensing provides another window into this hidden architecture. When light from distant galaxies passes through a foreground cluster, the degree of distortion reveals the total mass distribution, not merely the mass that emits or absorbs electromagnetic radiation. These measurements consistently show that galaxy clusters contain 5 to 6 times more mass than can be accounted for by their galaxies and hot intracluster gas combined. The dark matter forms a smooth, extended distribution that peaks at the cluster center and gradually decreases toward the outskirts, providing the gravitational well within which ordinary matter has collected. The cosmic microwave background offers perhaps the most precise measurement of the universe's dark matter content. The pattern of temperature fluctuations in this ancient light, released when the universe was only 380,000 years old, encodes information about the relative abundances of ordinary matter, dark matter, and dark energy. The acoustic peaks in the CMB power spectrum, measured with exquisite precision by satellites like WMAP and Planck, indicate that dark matter comprises approximately 26.8% of the universe's total energy density, while ordinary baryonic matter accounts for only 4.9%. The remaining 68.3% consists of dark energy, the mysterious component driving the universe's accelerating expansion. These observations constrain the properties that dark matter must possess. It interacts gravitationally, as evidenced by its effects on galaxy rotation, cluster dynamics, and light bending. It does not interact electromagnetically, or it would emit, absorb, or scatter light in detectable ways. It must be cold, meaning its particles moved slowly compared to the speed of light in the early universe, allowing it to clump gravitationally on the scales necessary to seed galaxy formation. Hot, dark matter, composed of fast-moving particles, would have smoothed out the density fluctuations needed to form the structures we observe today. Computer simulations have become essential tools for understanding how this cold, dark matter shapes cosmic architecture. The Millennium simulation, completed in 2005, tracked the gravitational evolution of 10 billion dark matter particles within a cubic volume 2.4 billion light-years on a side, following their motions from the early universe to the present day. More recent simulations, including Illustris, Eagle, and Illustris TNG, have incorporated the physics of ordinary matter alongside dark matter, modeling gas dynamics, star formation, supernova feedback, and black hole growth within the gravitational framework established by the dark component. These simulations begin with initial conditions derived from the cosmic microwave background, tiny density fluctuations imprinted during the inflationary epoch that followed the Big Bang. Dark matter particles, distributed according to these primordial perturbations, begin to fall toward regions of slightly higher density. Because dark matter does not interact with radiation, it can begin this gravitational collapse earlier than ordinary matter, which remains coupled to photons until the universe cools sufficiently for neutral atoms to form. By the time ordinary matter is released from this photon drag, dark matter has already begun constructing the gravitational scaffolding that will guide baryons into galaxies. The simulations reveal a hierarchical process of structure formation. Small dark matter halos form first, merging over cosmic time into progressively larger structures. A typical galaxy-sized halo today has experienced dozens of major mergers and absorbed hundreds of smaller halos throughout its history. This merger tree, as cosmologists call it, explains why large galaxies like the Milky Way are surrounded by satellite galaxies, and why galaxy clusters contain thousands of member galaxies, each representing a dark matter halo that has fallen into the larger cluster potential. The filamentary structure of the cosmic web emerges naturally from these simulations. Dark matter flows along paths of least resistance, streaming from underdense regions toward the nearest overdense nodes. Where these flows converge, filaments form, channels of enhanced density that connect the massive halos at their endpoints. The simulations predict that approximately half of all dark matter resides in these filaments, with another 40% concentrated in the halos of clusters and groups, and the remaining 10% scattered through the voids. Comparing simulated cosmic webs to observed galaxy distributions reveals remarkable agreement. The statistical properties of the simulated matter distribution, including the correlation function that measures how clustering strength varies with scale, match observations with impressive fidelity. The abundance of galaxy clusters as a function of mass, the distribution of void sizes, the typical lengths and thicknesses of filaments, all these quantities predicted by cold, dark matter simulations align with measurements from galaxy surveys spanning billions of light-years. Yet the simulations also reveal structures that remain largely invisible to optical telescopes. The dark matter filaments connecting galaxy clusters should contain vast quantities of ordinary matter as well, gas that has fallen into these structures but has not yet condensed into galaxies. This warm, hot intergalactic medium, heated to temperatures between 100,000 and 10 million Kelvin, emits primarily in the ultraviolet and soft X-ray portions of the spectrum, making it extraordinarily difficult to detect. Recent observations using fast radio bursts as probes of intervening matter have begun to confirm the presence of this missing baryonic component. finding that the total amount of ordinary matter in the universe matches theoretical predictions when this diffuse intergalactic gas is properly accounted for. The dark matter scaffolding also explains why the cosmic web maintains its structure despite the universe's expansion. Within filaments and clusters, the gravitational attraction of dark matter has overcome the cosmic expansion, creating bound structures that will persist indefinitely. In the voids, where dark matter density falls below the cosmic average, expansion dominates, causing these regions to grow emptier over time. The boundary between these regimes, where gravitational attraction precisely balances cosmic expansion, defines the edges of the structures we observe, the surfaces where matter has stopped falling inward and begun flowing outward with the Hubble expansion. The structures that dark matter has sculpted across cosmic time carry within them an even more ancient signature, a pattern frozen into the distribution of matter when the universe was less than 400,000 years old. This pattern, imprinted before the first stars ignited, before the first galaxies coalesced, provides a cosmic ruler that astronomers use to measure the universe itself. The baryon acoustic oscillations, as these frozen sound waves are called, represent the echo of processes that occurred when the cosmos was still a plasma, when light and matter were locked together in a single vibrating fluid. To understand these oscillations requires traveling back to an era when the universe looked nothing like it does today. In the first moments after the Big Bang, temperatures exceeded billions of degrees, and matter existed as a soup of fundamental particles, electrons, protons, neutrons, and photons all interacting continuously. The photons, particles of light, scattered constantly off the free electrons, unable to travel more than a short distance before colliding with another charged particle. This scattering bound the photons and the ordinary matter together into a single fluid, a plasma that filled all of space with a density billions of times greater than the densest material on Earth today. Within this primordial plasma, gravity began its work. Regions where dark matter had concentrated slightly more densely than average began pulling ordinary matter toward them. But unlike dark matter, which interacts only through gravity, the ordinary matter was coupled to the photons, and photons exert pressure. As matter fell toward the dark matter concentrations, the photon pressure resisted, pushing back against the compression. This created a tension between gravitational attraction pulling inward and radiation pressure pushing outward, and this tension generated waves, actual sound waves propagating through the plasma at roughly 60% of the speed of light. These were not sound waves like those that travel through air on Earth, which move at a mere 340 meters per second. The sound speed in the primordial plasma reached approximately 170,000 kilometers per second, fast enough to cross the current diameter of Earth's orbit around the Sun in less than 3 hours. At this tremendous speed, the waves expanded outward from each initial overdensity, carrying ordinary matter with them in spherical shells that grew larger with each passing moment. The waves continued propagating for approximately 380,000 years, the entire duration of the plasma epoch. During this time, each initial overdensity generated an expanding shell of compressed ordinary matter, while the dark matter remained concentrated at the center, unaffected by the photon pressure that drove the waves. The shells expanded to a radius of approximately 150 megaparsecs in comoving coordinates, a distance that accounts for the subsequent expansion of the universe. In physical terms, at that epoch, the shells had reached roughly 450,000 light-years across. But the stretching of space over the following 13.8 billion years has expanded this characteristic scale to its current size. Then, quite suddenly by cosmic standards, the waves stopped. As the universe expanded and cooled, the temperature dropped below approximately 3,000 Kelvin, cool enough for electrons to combine with protons and form neutral hydrogen atoms. This transition, called recombination, freed the photons from their constant scattering. Light could suddenly travel in straight lines across the universe, and the pressure that had driven the acoustic waves vanished. The shells of ordinary matter, caught mid-oscillation, froze in place. The pattern of compressions and rarefactions that had been propagating through the plasma became locked into the distribution of matter, a fossil record of those ancient sound waves. The signature of these frozen waves persists today in the distribution of galaxies across the universe. When astronomers measure the distances between millions of galaxies, they find a slight statistical excess of galaxy pairs separated by approximately 150 megaparsecs. This is not a sharp peak, but rather a gentle enhancement. Roughly 5% more galaxy pairs at this separation than would be expected from a random distribution. The effect is subtle, requiring surveys of hundreds of thousands of galaxies to detect reliably. But it has been measured with exquisite precision by projects like the Sloan Digital Sky Survey and the Dark Energy Survey. The physics behind this excess is straightforward once the acoustic oscillations are understood. Each initial dark matter overdensity in the early universe became the seed for a galaxy or galaxy cluster, and the shell of ordinary matter that expanded outward from each seed also became slightly overdense, creating a second preferred location for galaxy formation. The result is a universe where galaxies are slightly more likely to be found at the characteristic acoustic scale from other galaxies, a cosmic preference for a specific separation distance that has persisted for billions of years. This characteristic scale serves as a standard ruler for cosmology. Because the physics of the early universe is well understood, astronomers can calculate precisely how large the acoustic shells should have grown before recombination. By measuring the apparent size of this scale at different cosmic epochs, they can determine how the universe has expanded over time. If the measured scale appears smaller than expected, the universe has expanded more than predicted. If it appears larger, expansion has been slower. These measurements have provided some of the strongest evidence for dark energy, the mysterious component that is accelerating the cosmic expansion. The baryon acoustic oscillations also appear in the cosmic microwave background, the radiation released when the universe became transparent at recombination. The temperature variations in this ancient light, measured to precisions of 1 part in 100,000 by satellites like the Planck mission, show a characteristic pattern of peaks and troughs when analyzed by angular scale. The first peak, appearing at an angular scale of approximately 1 degree on the sky, corresponds to regions that had completed exactly 1/2 of an acoustic oscillation by the time of recombination, reaching maximum compression just as the waves froze. The second peak, at smaller angular scales, corresponds to regions that completed a full oscillation, returning to their initial density. Higher peaks trace regions that completed multiple oscillations, each peak slightly smaller than the last, due to the damping effects of photon diffusion. The positions and heights of these peaks encode fundamental properties of the universe. The angular scale of the first peak reveals the geometry of space itself, confirming that the universe is spatially flat to within 1%. The relative heights of odd and even peaks measure the ratio of ordinary matter to dark matter, showing that dark matter outweighs ordinary matter by approximately 5-to-1. The damping of higher peaks constrains the density of ordinary matter with remarkable precision, yielding a value of approximately 4.9% of the total cosmic energy density. These measurements from the cosmic microwave background and from galaxy surveys agree with each other to within their uncertainties, a remarkable consistency that validates our understanding of cosmic evolution from the plasma epoch to the present day. The same acoustic scale that appears as temperature variations in light released 13.8 billion years ago also appears as clustering patterns in galaxies observed today, stretched by the same factor that the universe itself has expanded. This agreement represents one of the great triumphs of modern cosmology, connecting observations separated by nearly the entire age of the universe through a single coherent physical framework. The baryon acoustic oscillations reveal something profound about the relationship between the very large and the very small in cosmology. The characteristic scale of 150 megaparsecs, spanning distances that light requires nearly 500 million years to cross, originated from quantum fluctuations in the first fraction of a second after the Big Bang. These microscopic variations in density, stretched to cosmic scales by the rapid expansion of inflation, provided the seeds around which the acoustic waves propagated. The largest patterns in the universe thus trace their origins to the smallest scales imaginable, a connection that spans more than 60 orders of magnitude in size. These acoustic oscillations, frozen into the fabric of space when the universe was barely 400,000 years old, provided the gravitational seeds around which matter would accumulate over the following billions of years. The slight overdensities they created, regions where matter was perhaps 1 part in 10,000 denser than average, became the nucleation points for the largest coherent structures that would eventually emerge from the cosmic web. Among these structures, galaxy walls represent some of the most striking departures from uniformity. Vast planar concentrations of matter that stretch across hundreds of millions of light years while remaining remarkably thin in the perpendicular direction. The Sloan Great Wall stands as one of the most thoroughly mapped examples of these enormous structures. Discovered in 2003 through systematic analysis of data from the Sloan Digital Sky Survey, this wall extends approximately 1.37 billion light-years in its longest dimension, making it one of the largest known structures in the observable universe at the time of its discovery. The wall lies at a distance of roughly 1 billion light-years from Earth, its light having traveled across space for a substantial fraction of the universe's current age before reaching our telescopes. Within this vast structure, thousands of galaxies cluster together in a flattened distribution, their positions tracing out a sheet-like geometry that defies the assumption of perfect cosmic uniformity. The formation of such walls follows naturally from the physics of gravitational collapse acting on the primordial density field. When matter begins to fall toward overdense regions under the influence of gravity, the collapse does not proceed uniformly in all directions. Instead, matter tends to collapse fastest along the shortest axis of any initial overdensity, creating flattened structures before spherical ones. This phenomenon, known as the Zeldovich approximation after the Soviet physicist who first described it mathematically, explains why the cosmic web contains so many sheet-like and filamentary structures rather than simply spherical concentrations of matter. The Sloan Great Wall contains within it numerous galaxy clusters and superclusters, each representing a local concentration of matter within the broader wall structure. The Shapley Supercluster, one of the most massive concentrations of galaxies in the nearby universe, forms part of this extended structure. With a mass estimated at approximately 10 million billion solar masses, the Shapley concentration alone contains enough matter to noticeably affect the motion of galaxies throughout a substantial volume of space. The gravitational influence of such massive structures creates the peculiar velocities that allowed astronomers to map the boundaries of Laniakea and similar superclusters. Mapping these walls requires systematic surveys that measure both the positions and distances of hundreds of thousands of galaxies. The Sloan Digital Sky Survey accomplished this by obtaining spectra for nearly 1 million galaxies, using the redshift of their light to determine their distances according to the Hubble-Lemaitre law. When these three-dimensional positions are plotted together, the wall-like structures emerge clearly from the data, appearing as dense concentrations of points separated by vast empty regions. The contrast between the walls and the voids they border can be striking, with density differences of a factor of 10 or more between the most crowded and most empty regions. The thickness of the Sloan Great Wall, while substantial in absolute terms at roughly 80 million light-years, remains remarkably small compared to its length. This aspect ratio of nearly 20:1 gives the structure its wall-like character, distinguishing it from the more spherical concentrations found in individual galaxy clusters. The thinness of such walls reflects the physics of their formation, where gravitational collapse has proceeded much further in some directions than others. Matter continues to flow onto the wall from the surrounding voids, gradually increasing its density while maintaining its flattened geometry. Within the Sloan Great Wall, the distribution of galaxies is far from uniform. Dense clusters containing hundreds or thousands of galaxies punctuate the structure at irregular intervals, connected by thinner filaments and sheets of more sparsely distributed galaxies. These clusters represent the nodes where multiple filaments intersect, concentrating matter through the convergence of gravitational flows from different directions. The Able Catalogue of Rich Galaxy Clusters identifies dozens of such concentrations within the Sloan Great Wall, each one a gravitationally bound system in its own right, while simultaneously forming part of the larger wall structure. The existence of structures as large as the Sloan Great Wall raises important questions about the limits of cosmic structure. The cosmological principle, which underlies most models of the universe, assumes that matter is distributed homogeneously when averaged over sufficiently large scales. This assumption proves remarkably accurate when applied to volumes larger than about 300 megaparsecs, roughly 1 billion light-years. At smaller scales, however, the universe displays significant departures from uniformity, with walls, filaments, and voids creating a complex pattern of overdense and underdense regions. The Sloan Great Wall approaches but does not exceed this homogeneity scale, suggesting that it represents one of the largest coherent structures that gravitational physics can create, given the age of the universe and the amplitude of primordial density fluctuations. Structures significantly larger than this would require either more time to form or stronger initial density contrasts than observations of the cosmic microwave background suggest existed in the early universe. The baryon acoustic oscillation scale of 150 megaparsecs provides a natural reference point, and the Sloan Great Wall spans roughly 9 times this characteristic length. Other galaxy walls have been identified throughout the observable universe, each one representing a similar concentration of matter into a flattened geometry. The CFA-2 Great Wall, discovered in 1989 through the Center for Astrophysics Redshift Survey, was the first such structure to be recognized. Located at a distance of approximately 200 million light-years, this wall appears prominently in maps of the nearby universe, stretching across the constellations of Coma Berenices and Leo. The Coma Cluster, one of the nearest rich galaxy clusters to the Milky Way, sits within this wall, its 1,000-plus galaxies forming a dense concentration within the broader sheet-like structure. The discovery of these walls transformed our understanding of cosmic structure. Before systematic redshift surveys revealed the three-dimensional distribution of galaxies, astronomers had assumed that galaxies were distributed more or less randomly throughout space, with perhaps some tendency to cluster together in groups and clusters. The revelation that matter is organized into vast walls and filaments, separated by enormous voids, demonstrated that the universe possesses a far more complex architecture than previously imagined. This cosmic web pattern, with walls as one of its primary components, reflects the fundamental physics of gravitational instability acting over billions of years. The walls themselves are not static structures, but continue to evolve as cosmic expansion proceeds. Matter flows along the walls toward the densest concentrations, gradually building up the mass of galaxy clusters at the expense of the surrounding regions. Simultaneously, the expansion of space stretches the walls, increasing the distances between their component galaxies even as gravity works to draw them together. This competition between gravitational attraction and cosmic expansion determines the ultimate fate of these structures, with the accelerating expansion driven by dark energy eventually halting further growth. Observations of galaxy walls at different distances and therefore different cosmic epochs reveal how these structures have evolved over time. Walls observed at redshifts of 1 or higher corresponding to look-back times of 8 billion years or more, appear less pronounced than their counterparts in the nearby universe. The density contrast between walls and voids was smaller in the past, reflecting the ongoing process of gravitational amplification that has concentrated matter into increasingly prominent structures. This evolution matches the predictions of cosmological simulations with remarkable precision, providing strong support for the standard model of structure formation. The anisotropy introduced by these walls affects the distribution of matter on scales approaching the homogeneity limit. While the universe appears statistically uniform when averaged over volumes containing many walls and voids, individual observers located within a particular wall or void would measure slightly different values for cosmic parameters depending on their local environment. The density of matter within the Sloan Great Wall exceeds the cosmic average by perhaps 30%, while the voids bordering it contain only 10 to 20% of the average density. These variations, though modest compared to the density contrasts within individual galaxy clusters, persist across enormous volumes of space. The density variations that characterize structures like the Sloan Great Wall, impressive as they appear against the cosmic average, represent only intermediate examples of the universe's tendency to concentrate matter into coherent formations. At distances approaching 10 billion light-years from Earth, observations of gamma-ray bursts have revealed evidence for a structure so vast that it challenges the conventional understanding of how large cosmic formations can grow within the age of the universe. The Hercules Corona Borealis Great Wall, first identified in 2013 through statistical analysis of gamma-ray burst distributions, spans an estimated 10 billion light-years across the sky. This extent, if confirmed, would make it the largest known structure in the observable universe, exceeding the Sloan Great Wall by a factor of nearly 4. The structure occupies a region of space centered roughly 10 billion light-years away, meaning the light now reaching Earth departed when the universe was less than 4 billion years old, barely a quarter of its current age. Gamma-ray bursts serve as the primary tracers for this distant structure because they represent the most energetic explosions in the universe, visible across cosmological distances where individual galaxies fade below detection thresholds. These bursts, lasting from milliseconds to several minutes, release more energy in seconds than the Sun will emit over its entire 10 billion year lifetime. Most gamma-ray bursts originate from the collapse of massive stars, or the merger of compact objects like neutron stars, events that occur preferentially in regions of active star formation. The distribution of these bursts across the sky therefore traces the distribution of matter at the redshifts where they occur. The statistical analysis that revealed the Hercules Corona Borealis Great Wall examined the angular positions and redshifts of gamma-ray bursts detected over several decades of observation. In a universe with perfectly uniform matter distribution, these bursts should appear randomly scattered across the sky at any given distance. Instead, the data revealed a significant clustering of bursts within a particular region, spanning the constellations Hercules and Corona Borealis, concentrated at redshifts corresponding to distances between 9 and 11 billion light-years. The probability of such clustering occurring by chance in a homogeneous universe falls below 1%, suggesting a genuine overdensity of matter in this region. The physical interpretation of this clustering requires careful consideration of what gamma-ray bursts actually trace. These explosions occur in galaxies undergoing active star formation, which in turn correlates with the presence of dense gas and the gravitational potential wells that collect such gas. A concentration of gamma-ray bursts at a particular distance and direction implies a corresponding concentration of star-forming galaxies, which themselves trace the underlying distribution of dark matter. The Hercules Corona Borealis Great Wall, if it exists as a coherent structure, would represent an enormous overdensity in the dark matter distribution at that epoch. The estimated dimensions of this structure create tension with standard models of cosmic structure formation. At 10 billion light-years across, the Hercules Corona Borealis Great Wall would exceed the theoretical maximum size for gravitationally bound structures in a universe only 13.8 billion years old. Gravity propagates at the speed of light, meaning that opposite ends of a structure spanning 10 billion light-years cannot have been in causal contact since the Big Bang. The structure cannot be gravitationally bound in the conventional sense, as there has not been sufficient time for gravitational influence to propagate across its full extent. This apparent paradox admits several possible resolutions. The structure may not be a single coherent formation, but rather a chance alignment of several smaller independent structures along the line of sight. Projection effects can create the appearance of enormous structures when multiple distinct formations happen to occupy similar directions as viewed from Earth. The statistical significance of the gamma-ray burst clustering, while suggestive, remains insufficient to definitively rule out such coincidental alignments. Alternatively, the Hercules Corona Borealis Great Wall may represent an early-stage formation, a region of slight overdensity that has not yet collapsed into a gravitationally bound system, but will eventually evolve into one or more superclusters. The cosmic web contains many such protostructures, regions where matter is flowing together under gravitational attraction, but has not yet reached virial equilibrium. At the epoch corresponding to 10 billion light-years distance, the universe was younger and denser, with structures at earlier stages of their evolutionary development. The mass contained within this putative structure, if it exists as described, would exceed 10 to the 18th solar masses, roughly equivalent to several thousand Milky Way galaxies, multiplied by the mass of the entire Laniakea Supercluster. Such concentrations of matter would create significant gravitational effects on surrounding regions, drawing in material from neighboring volumes and contributing to the growth of the cosmic web at that epoch. The structure would represent a major node in the matter distribution of the early universe, a region where the primordial density fluctuations happened to align constructively to produce an unusually large overdensity. Confirming the reality of the Hercules Corona Borealis Great Wall requires observations beyond gamma-ray burst statistics. Direct detection of the galaxies and galaxy clusters that should populate such a structure remains challenging at these distances. where even the most luminous galaxies appear faint, and the angular resolution needed to distinguish individual systems exceeds current capabilities for wide-field surveys. Future observations with next-generation telescopes may reveal the galaxy populations within this region, providing independent confirmation of the matter overdensity suggested by gamma-ray burst clustering. The cosmic microwave background offers another potential probe of such distant structures. Massive concentrations of matter leave subtle imprints on the microwave background through the integrated Sachs-Wolf effect, where photons gain or lose energy as they traverse the gravitational potential wells of intervening structures. A structure as massive as the Hercules Corona Borealis Great Wall should produce a detectable cold spot in the microwave background, a region where photons have lost energy climbing out of the gravitational well. Searches for such signatures in existing microwave background data have yielded ambiguous results, neither definitively confirming nor ruling out the structure's existence. The implications of structures approaching 10 billion light-years in size extend to fundamental questions about cosmic homogeneity. The cosmological principle, which underlies most models of the universe's large-scale behavior, assumes that matter is distributed uniformly when averaged over sufficiently large scales. Observations of the cosmic microwave background support this assumption, showing temperature variations of only 1 part in 100,000 across the entire sky. Yet if structures as large as the Hercules Corona Borealis Great Wall exist, they would represent significant departures from homogeneity on scales approaching a substantial fraction of the observable universe. The transition to homogeneity, the scale above which the universe appears statistically uniform, has been measured through various methods to occur somewhere between 300 and 500 megaparsecs, roughly 1 to 1.6 billion light-years. Structures exceeding this scale should not exist if the cosmological principle holds strictly. The Sloan Great Wall, at 1.4 billion light-years, already approaches this limit. The Hercules Corona Borealis Great Wall, if real, would exceed it by nearly an order of magnitude. This tension between observation and theory drives ongoing research into the nature of cosmic structure at the largest scales. Some cosmologists have proposed modifications to standard models that would allow larger structures to form, perhaps through non-standard initial conditions or alternative theories of gravity. Others emphasize the statistical uncertainties in current observations, noting that the evidence for extremely large structures remains preliminary and subject to revision as more data accumulates. The universe at these scales reveals the limits of human observation and understanding. Structures spanning billions of light-years exist at the boundary between the known and the speculative, where the evidence remains fragmentary and interpretation uncertain. The Hercules Corona Borealis Great Wall may represent a genuine feature of cosmic architecture, a formation so vast that it challenges theoretical expectations, or it may dissolve upon closer examination into a collection of smaller, more conventional structures. Either outcome would advance understanding of how matter organizes itself across the largest accessible scales. The vast walls and filaments that trace the cosmic web occupy only a fraction of the universe's volume. Between these luminous structures, Filling the spaces where matter has evacuated over billions of years, lie the cosmic voids, regions of such profound emptiness that they challenge intuitive understanding of what space can contain. These voids are not merely the absence of galaxies, but active participants in cosmic evolution, expanding regions whose underdensity shapes the flow of matter across hundreds of millions of light-years. The physics of voids begins with the same density fluctuations that seeded clusters and superclusters. In the early universe, regions of slightly below average density experienced weaker gravitational attraction than their surroundings. While overdense regions pulled matter inward, collapsing under their own gravity, underdense regions lost matter to their denser neighbors. This asymmetry amplified over cosmic time. A region that began with 99% of the average density found itself increasingly depleted as surrounding structures drew away its sparse material. The void grew emptier while the walls and filaments bordering it grew denser, a gravitational sorting process that has operated for nearly 14 billion years. The Botas void, discovered in 1981, provided one of the first dramatic demonstrations of cosmic emptiness. Spanning approximately 330 million light-years in diameter, this roughly spherical region contains so few galaxies that early surveys found only about 60 within its entire volume. For comparison, a sphere of similar size centered on the Milky Way would contain thousands of galaxies. The density within the Botas void falls to roughly 10% of the cosmic average, meaning that 90% of the matter that statistical expectation would place there has migrated elsewhere, drawn outward by the gravitational pull of the surrounding cosmic web. The KBC void, named after its discoverers Keenan, Barger, and Cowie, encompasses an even larger region that may include our own position in the universe. Estimates suggest this underdense region spans approximately 2 billion light-years in diameter, with the Milky Way and the entire Laniakea Supercluster potentially residing within its boundaries. The density within the KBC void measures roughly 20 to 30% below the cosmic average, a modest underdensity by void standards, but significant enough to affect measurements of cosmic expansion. If confirmed, our location within this void would mean that local measurements of the Hubble constant might differ from the true cosmic value, as light traveling through underdense regions experiences different expansion rates than the universal average. The internal structure of voids reveals their evolutionary history. Unlike the relatively uniform emptiness that intuition might suggest, voids contain subtle substructure, faint tendrils of galaxies that trace the remnants of the primordial density field. These void galaxies tend to be smaller and bluer than their counterparts in denser environments, their star formation histories shaped by isolation rather than interaction. Without neighboring galaxies to trigger starbursts through gravitational encounters, void galaxies evolve more slowly, retaining larger reservoirs of unprocessed hydrogen gas. Studies of void galaxies provide windows into galaxy evolution in pristine conditions, uncontaminated by the environmental effects that dominate in clusters and groups. The expansion of voids follows predictable physics, but produces counterintuitive results. As matter evacuates from underdense regions, the gravitational pull within the void weakens further. allowing cosmic expansion to proceed faster than in denser environments. Voids effectively expand faster than the universe as a whole, their boundaries pushing outward as the surrounding structures continue to accrete matter. This differential expansion creates velocity flows, with galaxies near void boundaries experiencing peculiar velocities directed away from the void centers. The Botas void, for instance, generates outflow velocities of several hundred kilometers per second for galaxies along its periphery. The shapes of voids reflect the geometry of the surrounding cosmic web. Rather than perfect spheres, most voids approximate irregular polyhedra, their boundaries defined by the walls and filaments that contain them. Where multiple filaments converge, void boundaries indent. Where walls stretch thin, voids bulge outward. Computer simulations of cosmic structure formation reproduce this polyhedral geometry with remarkable fidelity, predicting void shapes that match observations when the same initial conditions and physical laws are applied. The agreement between simulated and observed void properties provides strong evidence that the standard cosmological model correctly describes structure formation across all scales. The void hierarchy mirrors the hierarchy of overdense structures. Just as galaxies group into clusters and clusters into superclusters, small voids nest within larger voids in a fractal-like pattern. The smallest voids, sometimes called mini-voids, span only a few million light-years and may contain no galaxies at all. These mini-voids cluster along the boundaries of larger voids, creating a foam-like texture at intermediate scales. The largest voids, supervoids spanning hundreds of millions of light-years, contain numerous smaller voids separated by faint walls and filaments, structures too tenuous to appear in all but the deepest surveys. The gravitational influence of voids extends beyond their boundaries through a phenomenon called the void-in-cloud effect. A void embedded within a larger, overdense region experiences competing influences, its natural tendency to expand opposed by the gravitational contraction of the surrounding structure. These embedded voids evolve differently from isolated voids, their expansion suppressed or even reversed as the parent structure collapses. The interplay between void expansion and structure collapse creates complex dynamics that simulations are only beginning to capture in full detail. Temperature measurements reveal the thermal state of void interiors. The sparse gas within voids, heated by the ultraviolet background radiation that permeates intergalactic space, reaches temperatures of approximately 10,000 to 100,000 Kelvin. Despite these seemingly high temperatures, the gas density falls so low that the total thermal energy within a void remains negligible compared to the kinetic energy of the few galaxies it contains. The void gas exists in a state of near-perfect ionization, its hydrogen atoms stripped of electrons by the ambient radiation field, rendering it invisible to most observational techniques. The role of voids in cosmological measurements has gained increasing attention as precision requirements have tightened. The integrated Sachs-Wolf effect, which describes how photons gain or lose energy as they traverse evolving gravitational potentials, produces measurable signatures in the cosmic microwave background when photons pass through voids. As a photon enters a void, it climbs out of a shallow gravitational well, losing energy. If the void expands during the photon's transit, the well becomes even shallower, and the photon cannot regain all its lost energy upon exit. This net energy loss produces cold spots in the microwave background aligned with foreground voids, a correlation that has been detected statistically in large surveys. The cold spot, a region of anomalously low temperature in the cosmic microwave background spanning approximately 10 degrees on the sky, may represent an extreme example of this void-induced cooling. Located in the direction of the constellation Eridanus, the cold spot corresponds to a supervoid at a redshift of approximately 0.15, placing it roughly 2 billion light-years distant. Whether this supervoid fully explains the cold spot's temperature deficit remains debated, with some analyses suggesting additional physics may be required. The investigation continues, with the cold spot serving as a test case for understanding how voids imprint themselves on the oldest light in the universe. The structures that fill the cosmic web, from the densest galaxy clusters to the emptiest supervoids, exist within a finite volume of space from which light has had time to reach us since the universe began. This volume, the observable universe, represents not a physical boundary in space, but a horizon of causality, a sphere defined by the finite speed of light and the finite age of cosmic time. Beyond this horizon, space continues, galaxies presumably exist, and the cosmic web extends, but no signal from those regions has yet had sufficient time to traverse the intervening distance. The observable universe thus represents our window onto cosmic structure, a sphere approximately 93 billion light-years in diameter that contains every object we have ever detected and every structure we have ever mapped. The diameter of this sphere exceeds what a simple calculation might suggest. Light has traveled for 13.8 billion years since the cosmic microwave background was released, which might imply a radius of 13.8 billion light-years. However, the universe has expanded continuously during that journey, stretching the space through which ancient photons traveled. A photon that began its journey from a distant galaxy, when the universe was young, has been carried along by this expansion even as it propagated toward us at the speed of light. The result is that the co-moving distance to the edge of the observable universe, the distance measured in today's expanded coordinates, reaches approximately 46.5 billion light-years in every direction. The full diameter spans roughly 93 billion light-years, or about 28.5 gigaparsecs, a volume that encompasses approximately 2 trillion galaxies, according to recent estimates that account for faint, distant populations invisible to earlier surveys. Within this sphere, the distribution of matter follows the patterns that have emerged throughout this journey through cosmic architecture. Galaxy clusters anchor the densest nodes, connected by filaments that stretch for hundreds of millions of light-years, surrounding voids that occupy most of the volume. The statistical properties of this distribution, the correlation functions that describe how galaxies cluster, the power spectrum that quantifies density fluctuations at different scales, remain consistent across the observable universe. Surveys that probe different directions on the sky, examining regions separated by billions of light-years, find the same fundamental patterns. The cosmic web in the direction of the constellation Virgo resembles the cosmic web toward Sculptor or Fornax, or any other direction, once the statistics are properly averaged. This large-scale homogeneity emerges gradually as the averaging scale increases. At scales below roughly 100 megaparsecs, the universe appears distinctly lumpy. Galaxy clusters, superclusters, walls, and voids create density contrasts that can exceed factors of 10 or more relative to the cosmic mean. The Sloan Great Wall, spanning over 1 billion light-years, represents a genuine overdensity, a region where matter has concentrated above the average. The Botas void, stretching 330 million light-years across, represents a genuine underdensity, a region evacuated to perhaps 10 or 20% of the mean cosmic density. These structures are real, measurable departures from uniformity. However, as the averaging scale grows beyond approximately 300 megaparsecs, these fluctuations diminish. A sphere of this radius centered on any random point in the observable universe contains, on average, the same amount of matter as a similar sphere centered elsewhere. The density contrast between different such spheres drops below a few percent. At scales approaching a gigaparsec, the universe becomes statistically homogeneous and isotropic, meaning that no direction is preferred and no location is special. This property, assumed as the cosmological principle in theoretical models, has been confirmed observationally through surveys of galaxy distributions, measurements of the cosmic microwave background, and counts of radio sources across the sky. The transition to homogeneity carries profound implications for the structures discussed in previous sections. The Hercules Corona Borealis Great Wall, if confirmed at its proposed scale of 10 billion light-years, would challenge this framework. A structure spanning more than 10% of the observable universe's diameter would represent a density fluctuation at scales where homogeneity should prevail. Current observations suggest that the largest confirmed structures, walls, and supervoid complexes spanning 1 to 2 billion light-years remain consistent with the expected statistical fluctuations in a universe that becomes homogeneous at larger scales. The apparent detection of larger structures may reflect projection effects, where multiple smaller structures along the line of sight create the illusion of a single enormous feature. The matter content within the observable universe has been measured with remarkable precision. Ordinary baryonic matter, the protons, neutrons, and electrons that compose stars, planets, gas clouds, and living organisms, constitutes approximately 4.9% of the total energy density. Dark matter, the invisible gravitational scaffolding that shaped the cosmic web, contributes roughly 26.8%. The remaining 68.3% consists of dark energy, the mysterious component driving the accelerating expansion of space. These proportions, derived from observations of the cosmic microwave background, supernova distances, and baryon-acoustic oscillations, define the cosmic inventory with uncertainties of less than 1%. Converting these percentages to absolute quantities reveals the scale of the observable universe's contents. The total mass of ordinary matter within the observable sphere reaches approximately 10 to the 53rd kilograms, equivalent to roughly 10 to the 80 protons and neutrons. This matter is distributed among an estimated 2 trillion galaxies, though this count depends sensitively on how faint and small a galaxy must be before it no longer qualifies for the census. The total number of stars exceeds 10 to the 24th, more stars than grains of sand on all of Earth's beaches, a comparison that has become standard precisely because it conveys the incomprehensible scale through familiar imagery. The observable universe also contains approximately 10 to the 89th photons, primarily in the cosmic microwave background radiation that fills all of space with a temperature of 2.725 Kelvin. These photons outnumber baryons by a factor of roughly 2 billion to 1, a ratio established in the first seconds after the Big Bang, when matter and antimatter annihilated, leaving a slight excess of matter and a vast sea of radiation. The cosmic neutrino background, released even earlier than the microwave background, contributes a comparable number of neutrinos, though these remain undetected directly due to their extraordinarily weak interactions with matter. The edge of the observable universe is not a wall or a barrier, but a horizon that recedes as time passes. Each year, light from regions slightly more distant reaches Earth for the first time, expanding the observable sphere by 1 light-year in radius. Galaxies that currently lie just beyond the horizon will eventually become visible, their ancient light finally completing the journey that began billions of years ago. However, the accelerating expansion driven by dark energy complicates this picture. Galaxies beyond a certain distance are receding faster than light can travel through the expanding space between us. These galaxies will never become visible regardless of how long we wait. The cosmic event horizon, distinct from the particle horizon that defines the observable universe, marks this boundary of eternal inaccessibility. The observable universe thus represents a snapshot of cosmic structure, a finite sample of what may be an infinite or vastly larger cosmos. The patterns within this sphere, the clusters and voids, the filaments and walls, the statistical homogeneity at the largest scales, presumably continue beyond the horizon in forms we cannot directly observe. The consistency of physical laws across the observable universe, the uniformity of element abundances in distant galaxies, the identical spectral signatures of atoms billions of light-years away, all suggest that the cosmos beyond our horizon resembles the cosmos within it. The observable universe, vast as it appears, may represent merely a local patch in a structure whose true extent remains forever beyond our direct knowledge. The patterns that extend beyond our cosmic horizon, whatever their true nature, must eventually give way to a fundamental principle that governs the universe at its largest scales. As observations probe ever greater distances, as surveys map ever larger volumes of space, a remarkable transition emerges in the character of cosmic structure. The walls and voids that dominate intermediate scales, the filaments that stretch for hundreds of millions of light-years, the superclusters that gather thousands of galaxies into gravitationally influenced regions, all these features gradually fade into statistical noise when viewed from sufficient distance. The universe, so richly textured at scales we can comprehend, becomes smooth and featureless at scales that challenge comprehension. This transition to homogeneity represents one of the most profound discoveries in modern cosmology. The scale at which it occurs, approximately 300 to 400 megaparsecs, or roughly 1 billion light-years, marks a fundamental boundary in cosmic architecture. Below this scale, structure dominates. Galaxy clusters clump together, voids carve out empty regions, filaments trace preferred directions through space. Above this scale, the universe becomes statistically identical in every direction, its density fluctuations averaging out to produce a cosmic medium of remarkable uniformity. This homogeneity scale represents not merely an observational convenience, but a deep truth about the physics that shaped our cosmos. The mathematical framework that describes this transition relies on correlation functions, statistical tools that measure how the density at one point in space relates to the density at another point some distance away. At small separations, these correlations remain strong. A galaxy found in one location dramatically increases the probability of finding another galaxy nearby, a consequence of the gravitational clustering that has operated for billions of years. The correlation function at separations of a few megaparsecs might indicate that galaxies are dozens of times more likely to be found near other galaxies than random chance would predict. This clustering reflects the hierarchical assembly of structure, the tendency of matter to fall into existing concentrations. As the separation distance increases, these correlations weaken systematically. At 10 megaparsecs, the excess probability of finding a galaxy near another galaxy has diminished substantially. At 50 megaparsecs, the correlation has faded to only a few percent above random. At 100 megaparsecs, the signal becomes difficult to distinguish from statistical noise. By 300 megaparsecs, the correlation function has effectively reached zero, meaning that knowledge of the density at one location provides no useful information about the density at another location that distant. The universe has lost its memory of local structure. This decorrelation reflects the finite time available for gravitational clustering to operate. Light traveling at 300,000 kilometers per second has crossed only about 46 billion light-years since the universe became transparent, and gravitational influences propagate no faster than light. Structures can only have formed through the gravitational attraction of matter within causally connected regions, volumes where information and influence have had time to propagate. The homogeneity scale roughly corresponds to the distance over which gravitational clustering has had insufficient time to create significant correlations, a boundary set by the age of the universe itself. The cosmological principle, the assumption that the universe appears the same from every location and in every direction when viewed at sufficiently large scales, finds its empirical justification in this observed homogeneity. This principle, long treated as a philosophical assumption necessary to make cosmology tractable, has been confirmed through decades of increasingly precise observations. The cosmic microwave background, that ancient light released when the universe was only 380,000 years old, shows temperature variations of only 1 part in 100,000 across the entire sky. These tiny fluctuations, seeds of all future structure, demonstrate that the early universe possessed remarkable uniformity. Modern galaxy surveys have extended this confirmation to the distribution of matter in the contemporary universe. The Sloan Digital Sky Survey, mapping over 1 million galaxies across a quarter of the sky, reveals that the average density of galaxies in any sufficiently large volume matches the average density in any other sufficiently large volume to within a few percent. The 2-micron all-sky survey, detecting infrared light from over 1 million galaxies distributed across the entire celestial sphere, confirms this isotropy in 3 dimensions. The universe truly does appear the same in every direction when viewed at scales exceeding the homogeneity limit. This uniformity constrains cosmological models with remarkable power. A universe that appeared significantly different in one direction than another at large scales would require explanation, some asymmetry in initial conditions, or some anisotropic physical process operating on cosmic scales. The observed isotropy, combined with the Copernican assumption that Earth occupies no special location, implies homogeneity throughout the cosmos. If every observer sees the same statistical properties in every direction, and if no observer occupies a privileged position, then the universe must possess the same statistical properties at every location. The homogeneity scale itself provides information about cosmological parameters. Its precise value depends on the expansion history of the universe, the density of matter and dark energy, the initial spectrum of density fluctuations generated during cosmic inflation. Measurements of where structure gives way to uniformity help constrain these fundamental quantities, providing independent checks on values derived from other observations. The concordance between different methods, the agreement between homogeneity scale measurements, cosmic microwave background analysis, supernova distance measurements, and baryon acoustic oscillation studies builds confidence in the standard cosmological model. Yet the transition to homogeneity raises profound questions about the nature of cosmic structure. The largest confirmed features, walls like the Hercules Corona Borealis Great Wall spanning billions of light-years, approach or perhaps exceed the homogeneity scale. Their existence challenges simple models of structure formation, suggesting that rare statistical fluctuations can produce coherent features at scales where the universe should appear smooth. These structures represent the extreme tail of the probability distribution, configurations that occur only once or twice within the observable universe, but are not forbidden by physical law. The relationship between the homogeneity scale and the observable universe's size carries cosmological significance. The observable universe spans approximately 93 billion light-years, while the homogeneity scale measures roughly 1 billion light-years. This ratio of nearly 100 means that the observable universe contains roughly 1 million independent homogeneity volumes, enough statistical samples to establish the average properties of the cosmos with considerable precision. Had the homogeneity scale been much larger, comparable to the observable universe itself, cosmology would face fundamental limitations. Measurements would reflect local peculiarities rather than universal properties. The smoothness at large scales connects to the physics of cosmic inflation, the hypothesized period of exponential expansion in the universe's first fraction of a second. Inflation stretched quantum fluctuations to cosmic scales while simultaneously smoothing out any pre-existing irregularities. The homogeneity we observe today reflects this primordial smoothing, modified by billions of years of gravitational evolution that amplified small initial variations into the structures we observe. Without inflation or some equivalent mechanism, the uniformity of the universe at large scales would require explanation, a cosmic coincidence demanding physical cause. Dark energy, the mysterious component driving the universe's accelerating expansion, influences the homogeneity scale through its effect on cosmic evolution. As dark energy increasingly dominates the universe's energy budget, it suppresses the growth of structure on large scales. Gravitational clustering, which would otherwise continue building ever larger configurations, finds itself opposed by the accelerating expansion that carries matter apart faster than gravity can draw it together. The homogeneity scale may thus represent not merely a current boundary, but an asymptotic limit, a maximum scale for structure in a universe destined for eternal acceleration. The future evolution of cosmic structure points toward increasing uniformity. As expansion continues, as dark energy stretches space ever faster, the density contrasts that define walls and voids will gradually diminish. Clusters will remain bound by their internal gravity, but the larger patterns that connect them will fade into the expanding void. The cosmic web, that intricate network of filaments and nodes, will slowly dissolve as its components drift beyond each other's gravitational reach. The homogeneity scale, rather than growing to encompass larger structures, will shrink to encompass smaller ones as clustering reverses under cosmic acceleration. This ultimate fate reinforces the transient nature of cosmic structure. The walls and filaments that seem permanent on human timescales represent a particular moment in cosmic evolution, a configuration that emerged from primordial smoothness and will eventually return to smoothness of a different kind. The universe began uniform, developed structure through gravitational instability, and will end uniform again as expansion overwhelms attraction. The homogeneity we observe at the largest scales today offers a preview of the homogeneity that will eventually characterize all scales in the distant future.